The first one is located at x is equal to 0. Another one is located at x is equal to L by 2. For this, it is located at L by 2 and L. Fine. So these limiting entities are referred as a node. Fine. So subdomain 1 has a 2 node. The first one is at x is equal to 0. The second one is at x is equal to L by 2. In the same way, the subdomain 2 also has a 2 limiting entities. The first one is located at L by 2. The another one is located at L. Now, what I'm saying that this is the node 1 of subdomain 1. This is the node 2 of subdomain 1. Then, in the same way, I am saying that this is the node 1 of the subdomain 2, while this one is the node 2 of subdomain 2. Fine. So this is 1, 2, 3. But if I look at globally, then this global FEA model has only 3 nodes, and that I am representing with the help of a different color. I am saying that this is the first node which is at x is equal to 0. This is the second node at x is equal to L by 2, where you have done the bisection of the whole domain into a 2 division. So at that line, there is one point which is dividing the domain into a 2 equal parts. So at that position, I have selected node 2, and at x is equal to L, there is another node that is 3. Fine. So where will you find the presence of node? First, at the limiting entities of the domain, that is at the 2 extreme location at x is equal to 0 and at x is equal to L. Fine. And at other locations where you have divided the whole domain into a subdomain. So wherever you will find the beginning of the subdomain or the end of the subdomain, you will have the nodes. Fine. So this 1, 2, 3 in a blue color represents the global node you have in your analysis, while this 1, 2 in a black color represents the nodes which are pertaining to subdomain 1 as well as the nodes which are pertaining to a subdomain 2. Fine. Now, at node 1, the value of primary variable, I will say that it is your UE1. At node 2, I will say the value of primary variable is UE2. Here, I will say it's a U21. And here I will say it's a U22. So this notation has the subscript value also as well as the superscript value also. So variable U has a subscript also, it has a superscript also. The subscript represents the node number, while the superscript represents the subdomain number. So if you see carefully, this superscript is 1. But then this is subscript 1 which is referring to a local node number 1. In the same way, here the superscript remains 1 because you are not changing the subdomain. You are in the still same subdomain. But the subscript has been changed because the position has been brought from the beginning to the end of the subdomain, and at end of the subdomain you have the presence of the local node, that is 2. So this is the notation practice that is referred in FEM. Fine. In the same way, you can refer to U21 and U22. U21 refers to the value of a primary variable at subdomain 2 at node 1, and U22 refers the value of a secondary variable in subdomain 2 at node 2. In the same way, fine, this node will have a certain communication from the rest of the world. We say that this communication is for subdomain 1 at node 1. In the same way, here also you will have some communication. We will say that this is for subdomain 1 at node 2. In the same way, fine, for subdomain 2 at node 1, we will say it's a Q21, and over here it's your Q22. Fine. So this is the philosophy. Now, in this generalized expression, I have written UE1. So what is this UE1? This E represents the subdomain number, and now it is clear that every subdomain has only 2 nodes for the linear distribution that you have chosen. So the node 1 is representing the value of a primary variable at node 1 of subdomain E. In the same way, if you write UE2, this indicates value of primary variable for subdomain E at node 2. In the same way, you can correlate for Q. Fine. So now if you observe this elemental relationship that I have written, it is representing the relationship between the primary variable and secondary variable. Fine. On the left side, you have the presence of primary variable. On right side, you have a presence of secondary variable. So when primary variable is multiplied to some material property, geometrical property, fine, it is giving you equal to some secondary variable. So there is a response between the primary variable and secondary variable. So this kind of thing we have to write for each and every element, and then we have to do the balance. Okay, now I want to write this kind of relationship for both subdomain, that is 1 and 2, and just for the sake of easiness, let us assume that C is equal to 0 and F is equal to 0. Which C? The small c equal to 0, and this F value is also 0. So with this, your elemental equation will reduce to a very simple form, that is your A E over H E into 1 minus 1 minus 1 1 plus into UE1 UE2, that is equal to your QE1 and QE2. Fine. Some of the author refers this as stiffness matrix. Fine. Then this as a displacement vector, it is referred as a force vector. The reason is that this finite element method basically originates from the structural engineering, and in early stage it has a wide application in the civil engineering field. That's why this notation is still popular, and they are referring this as a stiffness matrix. Then the vector on the left side is the displacement vector, and the vector on the right hand side is referred as a force vector. In terms of abbreviation, they used to write this way, that is the KE into UE, that becomes equal to your FE. So where KE is nothing but your A by HE into 1 minus 1 minus 1 and 1. So this is your stiffness matrix. Okay, now the way in which I have written the elemental relationship for the case where the small c is 0 and F is equal to 0, I can write this generalized form to the specifically for subdomain 1 as well as for the subdomain 2. Okay, I am adding pages. Okay, now once again go back to that original domain. So this is my overall domain, and I have the additional node over here. So I have a 1 over here, I have a 2 over here, I have a 3 over here, and my subdomains are first one over here, second one over here. And if I represent this in terms of the two subdomain, this is my first subdomain, and then this is my another subdomain, that is second one. This is first one, this is second one, and this has a local node 1, this has a local node 2, this has a once again local node 1, and this has a local node 2. Fine. And then in terms of primary variable notation, I am writing U11, this I am writing U12, this I am writing U21, and for this I am writing U22. And the interaction with the rest of the world also I am representing. So the interactions, let me change the color. It is Q11, here it will be Q12, here it will be Q21, and for this one it will be Q22. So this completes the subdomain representation. Fine. Also, this is called your global FEA model. This is called the representation of the same domain in a discrete way. Fine. So in a simple way, this is also referred as a grid generation or a mass generation. Fine. You have divided the whole domain into a two subdomain, and then you are saying that if you make an assembly of these two subdomain, you will have overall subdomain. Fine. Now, for the first element, I will try to write that elemental relationship. So now I am writing A1 upon H1. Then I am writing 1 minus 1 minus 1 1, and then in multiplication of this one you have a U11 U12, that is equal to, sorry, not plus, it is equal to your Q11 plus Q12. And then if you write it for the second subdomain, you have to write it A2 H2. Then this is 1 minus 1 minus 1 1 into, it is your U21 U22, that is equal to your Q21 and Q22. So the first elemental relationship is for subdomain 1, while the second elemental relationship is for subdomain 2. Here, this A1 is a value of a small a. This is also a value of a small a. There is a possibility that, fine, few things will change across the domain, so value of a might change. But if you have the constant property, constant cross-sectional area, then A1 and A2 will remain same. Fine. Then H1 and H2 refers to the length of the subdomain 1 and subdomain 2. In a present case, each subdomain has a length that is L by 2. But I have written in a general sense, if any variation is there, then this A1, A2 will have a different value, H1 and H2 will have a different value. Okay. Now, in present case, if we assume that there is no variation of geometrical parameter, there is no variation of the material properties, then A1 and A2 are same. And as we have chosen the equal subdomain length, the H1 and H2 will also same. So I will make necessary changes over here. Okay, I will rewrite. That is the most easiest way. Okay. So here, now I am writing A by H. And here also I am writing A by H. As A1, A2 are same and H1, H2 are same. Okay. So now this two equation needs to be assembled. That means I have to combine these two. Now, when you want to combine, you have to take care of few things. I will not go to the next slide. I will explain here only. Okay. Now, if you try to have the bottom-up approach, that means if you move from the subdomain approach to the domain approach, you will find that this first node of the second domain and the second node of the first domain, geometrically they are positioning at the second global node, that is written in the yellow color. Fine. That means the two primary variable that I have written, which two primary variable? This one, that is your U12 and U21. They are the values of variable for the same geometrical position referring to x equal to L by 2. So this is also representing the value of variable at location x is equal to L by 2. This is also referring to the value of a primary variable at geometrical location x is equal to L by 2. Fine. But still, they have a different notation. So what we have to do, we have to equate these two variable and replace suitably with a new variable. So what I am saying that these two variables are supposed to be same, because the value of a primary variable at a chosen location must have a unique value. If it does not have a unique value, it is called discontinuity. So your solution will be discontinuous. To explain you, let me draw one variation so that you will have the idea about the discontinuity. For the same two subdomain, let us say this is the variation of u with respect to x. And I have no idea, I am drawing it very randomly. So this is the variation over the first domain, that is between 0 to L by 2, and then there is another variation over the rest of the domain. So this is referring to, if this happens, that you have this as a u12 value and this as your u21 value, there will be a discontinuity that is called a gap. And in most of the engineering problems, the solution is supposed to be a continuous one. There cannot be a discontinuity in terms of primary variable. Otherwise, there is a sudden jump in the value of a primary variable. Fine. This normally happens in case of a normal shock. Fine. But in case of a structural problem, heat transfer problem, and normal fluid mechanics problem, you will always find that the solution is always continuous one. So this discontinuity should not exist. So for that, what I have to do, I have to say that my u12 should be equal to u21. And now I am referring to this as my u2, which is also true, because these two are referring to the value of a variable that node 2. And this mathematical expression is called the continuity of a primary variable. Fine. So your primary variable has to be continuous one. Then if you look at node 2, at node 2, that is global node 2, you have the exchange of information with respect to subdomain 1. You have the exchange of information with respect to a subdomain 2. That means this node is going to receive some information from subdomain 1. This node is going to give some information to a subdomain 2 that is having the common node 1. So the second node of the first subdomain is global node 2, and the first node of the second subdomain is also a global node 2. So at global node 2, some information is coming from the subdomain 1 with respect to node 2, and some information is taken by the subdomain 2 at node 1. Now, there is a possibility that some point source may be present over here, that I am saying Q2. Now, in case of a steady condition, no imbalance should exist anywhere inside the domain. For example, at any chosen location, you have an imbalance of a force, then the system will either try to elongate or the system will try to contract depending upon the nature of force. And this happens still the forces are balanced. If I talk about the thermal problem, if there is an imbalance of heat, then what will happen? The temperature will start increasing. So in terms of this requirement, all this secondary variable has to be balanced. Plus your Q21 is supposed to be equal to Q2. Fine. So this is as good as the vector summation of the information that is coming at node 2. It is also nothing but a simplified form of the Kirchhoff's law of current. Fine. Whatever is the sum of current, value for current that is leaving, fine, that should be ideally speaking equal to 0. If any imbalance between these two is there, then it is exactly of current that is generated at a point. So this is about the balance of secondary variable. So taking this 2 in mind, we have to do the assembly of the two equation that we have written. Which two equation? Okay. So this two equation that I have written, you have to assemble. Fine. And there are different approaches. Either you can write four equations with the help of two elemental relationship and then prepare the assembly, or you can do it in a direct way also. We will see the quickly both the approaches. Okay, so first what I am doing, I am writing the separate equations from each and every elemental relationship. So I am writing this way. It is your A by H into 1 into your U1, then minus A into H by U2. That is equal to, I am writing Q11. Then another equation I am writing this way, that is A by H. Sorry, here it will be minus. Then it's your U1 plus A by H into U2. This is equal to your Q12. Fine. How this first set of equation is obtained? This first set of equation is obtained by multiplying the rows and column vector of the first elemental relationship. Yeah, fine. If you do the multiplication of A by HE with this row and with this one, fine. Here I am replacing this U11 as a U1 and I have replaced this U12 with U1. And then if you do the multiplication, you will be able to equate this to Q11. For the second equation, do the multiplication of A by HE with the second row of the first elemental relationship. Fine. And then with U1 and U2, you will get equal to Q12. In the same way, repeat the procedure for the second elemental relationship. Okay, so you will have the second equation, and from the second elemental relationship you will get the two additional number of equation. What that will be? I am writing that one. That is A by. Okay, let me use a different color. Okay. So now that will be A by H into U2 minus A by H into U3. This turns out to be your Q21, and then you will have A by H minus, obviously, this is your U2 plus A by H of U3, that is equal to Q22. Fine. So these are the four set of equation. Fine. Now I will make use of balance of secondary variable. What is that one? It is Q12 plus Q21, that is equal to Q2. So to use this one, I will say that this is my first equation, this is the second one, this is the third one, and this is the fourth one. What I am doing, I am adding the equation number 2 and equation number 3. Fine, that is what I am doing. So now, okay, so I am adding equation number 2 and equation number 3, and I am leaving the equation 1 and equation 4 as it is. Fine, but what I will do, I will do the replacement of Q11 with Q1, and then I will be writing this one as a Q3. Fine. So first I will write the equation for Q1, then I will add Q12 plus Q21, and then I will write the equation for Q3. So now the equation for Q1 becomes A over H into U1 minus A over H into U2, that is equal to my Q1. Then I am adding this 2, that is Q11 plus Q12 I am adding. So what this will give me, it is a minus of A by H into U1 plus A by H of U2. Then I am using a different color just to make the difference between the first, that is the second equation that is coming from the first domain, and this first equation that is coming, sorry, third equation that is coming from the second subdomain. So now you have A by H into U2 minus A by H into U3. Okay, so now if you observe carefully, this is the contribution from the second equation, while the green color part is nothing but the contribution from the third equation. So it is as good as the red portion on the right side represents your Q11, while the green portion on the right side is representing your Q12. Fine. These two can combine together and return as, it is a minus of A by H into U1 plus 2 times A by H into U2 minus A by H into U3. And then the last one, that is the fourth equation, I will write as it is. It is minus of A by H into U2 plus A by H into U3. And this I am equating to Q3. Fine. So now I have, this is my fifth equation, this one is my sixth equation, and this one is my seventh equation. What can I do? I can write this three set of equation in terms of a matrix relationship. Fine. And that representation I am going to write. Okay, so if you write this three set of equation in terms of matrix relationship by taking the common terms out of all these three equation, you will have this kind of 3 by 3 matrix that is available on the left side. I will say it is 1, minus 1, 0, then minus 1, 2, 1, 0, minus 1, 1. This 3 by 3 matrix is multiplied to a vector of 3 primary variable, that is U1, U2, U3, and then this relationship is equated to a variable, that one is Q1, Q2, and Q3. For understanding, you can remember like this, that this is nothing but your Q11, this is equal to Q12 plus Q21, and the last one is nothing but equal to your Q22. So this completes your assembly of the elemental equation. Fine. Now only the information has to be substituted. This is known to you because this depends upon the geometrical information as well as the material information. So this is known to you. Fine. Then out of 3 primary variable and 3 secondary variable, 3 information should be known to you. then and then this becomes your well posed problems, otherwise it will become your ill posed problem. Fine. So this is all about solution procedure once you develop your elemental equation. And this procedure we are going to see in few examples. I have developed the solution of simple elementary problems that will give you the flavor of this procedure. And we will start with a very simple problem, and at the end we will consider one benchmark problem where you have all complications, obviously with respect to a one-dimensional analysis only. Okay, so yeah, this is the first problem that I would like to solve, and it's a very simple problem. It is having a two-step. This step structure is subjected to an axial load on the extreme right hand side, and the value of the axial load is 10 Newton. The left extreme end of the structure is constrained. That means it is fixed. This end does not have a freedom to move. While at the extreme right hand side, the forces are applied and it has a freedom to move. Either it will be elongated or it will be contracted. Fine, depending upon the direction of the force that has been applied. Okay, then the length of the first larger step is given as 100 mm. Its cross-sectional area is 20 mm square. Fine. E1 is 210⁻³ megapascal. This value, please correct. This will be 10 millimeters square. This is not 20. Let me check. It's a 4 into 10⁻⁴. The second one is 2 into 10⁻⁴. So yeah, obviously this is 20. Fine. So consider A2 as a 10 millimeter square. Just a minute. Okay, so this cross-sectional area for the second step is 10 millimeters square. For the first one, it is 20 millimeters square. The material property is same, but there is a change in cross-section. So if I want to solve this example with our second order model boundary value problem, fine, we have to first find the appropriate differential equation. And for this case, the appropriate differential equation is having this form, that it is a minus of d by dx into AE into du by dx, that is equal to 0. This is the appropriate differential equation which is valid for the one-dimensional axially loaded bar problem. Here A stands for the cross-sectional area, E stands for modulus of elasticity, U stands for the displacement. And on a structure, you don't have the axially distributed load. There is nothing like the axially distributed load. So F is 0. And C is also 0 because C part is also absent in governing differential equation. So with this form of differential equation, you can always say that small c equal to 0, small f is also equal to 0. And our objective is to find out displacement, stress and strain for axially loaded bar. So once the physics of the problem is clear to us, the differential equation either you derived or you obtain with the help of the literature or by referring it to a suitable textbook, you can start solving this problem. What is the first step? The first step is to generate appropriate number of a subdomain. and this is called a grid generation or a mesh generation. Here I am considering one subdomain for each and every step. So as I have a two step, fine, I am considering subdomain 1 inside a larger step, and I am considering the subdomain 2, fine, for a smaller substep which has a cross sectional area of 10 millimeters square. Okay, then we have to represent that if you make an assembly of these two subdomain, it becomes your overall domain of the analysis. So the element 1, which is now referred to a larger cross-sectional area, element 2, which is now referred to a smaller cross-sectional area, when these two are combined together, that means with addition, they are representing to a total domain of the problem. Fine. So this is the elemental representation of the problem. Each and every element is represented separately. Fine. And whatever geometrical and the material properties are true for that subdomain, that is exactly written below the geometry of the subdomain. And then below this one is nothing but your FEA model. This is referred as a FEA model, where the subdomain 1 and 2 is written on the top of the one-dimensional element. The global node numbers are also written as 1, 2, and 3. Fine. So this is referred as your FEA model. So a global FEA model also has to be prepared. Now, then exactly below the each and every element or a subdomain, fine, the elemental representation is done. This is what we have discussed, that for every element or every subdomain, there are two limiting entities, that is local node 1 and local node 2. See the color has been changed, and these two are referred as a local node number because they are always referred with respect to a which subdomain. Here also you have a local node number 1 and 2, but obviously these are referred to a second subdomain, that is numbered 2. And the primary variable also has a notation that is indicated with the help of a superscript and subscript. Superscript always referred to element number and subscript always referred to a local node number. Okay, so this is the elemental representation. Write all local node number represent all primary variable and secondary variable with respect to that local node number for that subdomain. Okay, then development of the elemental equation. As we have already developed this kind of elemental equation, you don't have to separately develop. Fine. So this is your elemental representation for element 1. And then this is the matrix relationship for the element 1. And this is also called element equation in a matrix form. This you have to write or you have to develop. Okay, if you observe carefully, then on the top of each and every stiffness matrix, I have written number 1 and 2. And this notation has a different color. The number 1 and 2 is written in terms of black color also. Number 1 and 2 is written in terms of blue color also. The numbers which are written in a black color refers to a global node number, and the numbers which are written in terms of blue color is referred to a local node number. On the same way, the similar number writing pattern has been observed on the right hand side of the relationship, that is 1 2 in terms of blue color, 1 2 in terms of a black color. Fine, that also has the same meaning, that is global node number and local node number. Fine, so this relationship is now familiar to you, so I am not discussing in detail. So the way in which I have done the representation for element 1, you have to do it for the second element also. And here also the color pattern and writing the variable is same. So I am following the same pattern for writing the primary variable as well as for writing the secondary variable. Okay, once you write the elemental relationship for element 1, element 2, now you have to make an assembly. Fine. So now two subdomains are represented side by side with subdomain 1 and subdomain 2. And then these two are joined over here. Fine. The subdomain 1 and subdomain 2. It is as good as the subdomain 2 has been dragged and pulled towards the subdomain 1 till the first node of the subdomain 2 overlaps or matches with the second local of the first subdomain. And because of this, there will be an overlapping of the primary variable, that is u12, and the primary variable u21. And as I told you that these two primary variables are referring to a same variable at global node 2, it cannot be having a different value, and that is referred as a continuity of a primary variable. So this condition has been put in terms of the mathematical expression, that is u12 is equal to u21, that is equal to u2. This is called continuity of a primary variable. And then to have the stability, all the secondary variable has to be balanced, and it is called balance of secondary variable. In terms of mathematics, this has been written in terms of f12 plus f21, that is equal to f2. You can correlate this equation to q1 that we have discussed. So this two condition has to be met when you make an assembly of the elements. Okay, then preparing the global matrix. The one method that we have seen, there is another method also. Okay, for that I will use an additional slide. Okay, preparing the global matrix, you have seen one method wherein the four equations are derived from these individual with the help of the balance together, and then it becomes your 3/3 relationship. Now every time you don't have to do this one. Fine, you can write it quickly also. So I am going to show you the shortcut method. Let me first write quickly the elemental relationship for subdomain 1. So I am writing this way, that is, it is your A1 by H1. I am assuming A1 and H1 different for subdomain 1 and 2. So this one is my 1, minus 1, minus 1, 1. Fine. That is equal, sorry, in multiplication of your U11 and then U12. So now, as the continuity of primary variable is known to you, fine, there is no need to write the subscript. You can eliminate writing the subscript. So there is no need to write the subscripts with the superscript. Instead of that, you can directly write the notation, that is U1 and U2. I am writing this way, it is U1, it is U2. That is equal to, you have the Q11, still I am referring to the secondary variable with a superscript and subscript notation. There is a reason behind it. Okay, for second one, this will be A2, then H2, and you have the similar term, that is 1, minus 1, minus 1, 1. Here you will have the U2, and here you will have a U3. So this is still in terms of the local notation, that is U21 and U22. Okay, now I will write the global degrees of freedom, that this subdomain 1 is between global node 1 and 2. This is also between a global node 1 and 2. The subdomain 2 is between global node 2 and 3. This is also between a global node 2 and 3. Fine. Now, if you refer to the problem, how many global nodes you have? We have 3 global nodes. That means the number of primary unknowns are only 3. That is U1, U2 and U3. So the size of the global matrix will be decided by the total number of primary variables that is not known to you, or you want to find out the information about the total number of primary variables. So in a present case, we have only three primary variables which are unknown. So the size of the global matrix will be 3 by 3. So what I am writing, I am first preparing a square matrix on the left side. And obviously this will have a size of 1, 2 and 3 row. And this will be multiplied with the vector of primary variable, that is u1, u2 and u3. Fine. And on the right hand side, you will have some secondary variable. How to get that we will discuss quickly. Okay. Now, this also represents global node number. This also represents a global node number. Now, I have to find out what are the entries over here, as well as over here and here. Fine. Now, to find out the entries, what I will do, I will refer to the elemental matrix relationship. Here you have a first column, you have a first row, and at the intersection of this first row and first column, you have the 1. Obviously, this 1 is going to multiply by this value, that is A1 by H1. So this entry I will write over here with sign, that is A1 by H1. In the same way, for the second column and first row, the entry is -1. So I am going to write -1 into this A1 by H1 over here. And there is nothing like a third column with respect to a first row, so I will have a 0. So this completes the entry of the first row. Then for the second row, if you observe carefully, here it will be -A1 over H1. Then here you will have a 2 entries. The first one is from the first relationship. The second one is from the second relationship. Fine. So this A1 H1 is because of this one. And this A2 by H2 is the intersection of the second column and the second row. Fine. So this is A2 by H2. Then intersection of third column, second row is -A2 by H2. Here it will be 0. This will be -A2 by H2 and this will be your A2 by H2. So this completes preparation of a global matrix. Here obviously you will have a Q11. Here you will have a summation of Q12 plus Q21 and then here you will have a Q22. And later on, you can replace this Q11 as Q1. This will be equal to Q2 and the last term can be equal to Q3. That is the global interaction for the FEA model. So in this way also you can prepare your global matrix. Fine. Whichever is suitable to you, that procedure you can adopt. Okay, so now let's go ahead. Okay, so this is the assemble matrix that we have prepared. Now, if you observe carefully, this assemble matrix represents only 3 equations. That means at the most you can have the information about 3 variables, and at present you have a total 6 variables. 3 in terms of primary variable, 3 in terms of secondary variable. So out of this 6 variable, the information about the 3 variable has to be fetched or it has to be obtained. Who will help us? The constraint boundary condition of the problem will help us. Let us once again refer back to the problem. Yeah, this is my problem. Now, at this point, your u value is 0. That means displacement is not possible. And this physical location is coinciding with the global node 1. So I can say that my u1 will be 0. Then at node 3, the some force value is given to you. So I will say that this is my F3. And as the force is applied in positive x direction, fine, it is having the positive value, that is 10 Newton. At this node, you have the presence of global node 2. Fine. So I will say that U2 is not known to me. U2 I have to find. Is there any possibility about getting F2 information? First, is there any local F2 that is applied at point 2? No. Fine. So if that is the case, that no local force values are applied at a node, you can safely write that F2 equal to 0. Fine. So how many information we have fetched? We have fetched three information, that is U1 equal to 0. Second, F3 is 10 Newton. And the third one, that is F2 equal to 0. So now out of 6 variables which were not known to you, about 3 the information has been derived or it has been fetched. The remaining 3 you have to obtain from the global relationship. Okay, so now this U1 is known to you. Whichever is known to me, I am just putting the tick. This is known to me. Fine. Then about F2, I have some information. F3 also, I have some information. So only 3 variables are unknown. That is this F1, U2 and U3. So for this 3 variables, I have to solve the 3 sets of equation. So now this becomes your well-posed problem, because the unknowns are 3, equations are 3. If you have the vice versa situation wherein the number of unknowns are less than the number of equation, then multiple solution is possible. And when you have the number of equation which is lesser than the number of unknown, then you can say it's a ill-posed problem, the solution is not possible. Fine. So in case of utilizing finite element method, you have to make sure that fine, the number of unknowns are exactly equal to the number of equation that you have at the end of the assembly. Now, okay, so now whatever is known to you, you substitute that into this global relationship. Fine. And with boundary condition, that is U1 equal to 0, F3 is equal to 10 Newton, then you rewrite all this so that you have 3 equation. Now this 3 equation has to be solved for 3 unknown, that is F1, U2 and U3. There are many ways in which you can solve it. I will not go into that detail. But if you develop the solution of this 3 set of numerical equation, you will get the information about U2, you will get the information about U3, and you will get the information about F1. Exactly equal and opposite in direction. Fine. It should be exactly equal and in opposite direction. Just a minute. Okay, so with the help of the available three set of equation, you can obtain the information about the three unknowns. And for this problem, you will have U2, U3 and F1 as an unknown, and this solution procedure will give you that information. So once you have the primary variable information, that is U2, U3, you will get the values of strain, stress, because reaction you have already obtained. So now the only information that you have to obtain is the strain distribution and the stresses. This can be easily obtained. Fine. The strain for the first element can be written as the difference of displacement at a two node divided by the distance between the node. So this will give you a strain in the first element. Using the similar equation, you will be able to obtain the strain in the second element. And once you have the strain value, you multiply that with a modulus of elasticity, you will get the stress in the first element. Obviously, using the same procedure, you will get the stress values in the second element also. Fine. Now, if you observe carefully, the value of a stress in the first element is much more smaller compared to the value of a stress in the second element. The reason is that there is a difference in cross section. The first step is having the larger cross section compared to the second one. Fine. So the region where you have a larger cross section, obviously the low stress value will come. A region in which you have a low cross sectional value, where you will have the larger stress value. So this is as per the physics of the problem, and there is nothing wrong in it. So this completes your solution part, and this simple example also helps you to understand the different procedural aspects that is involved in solving any problem with the help of a finite element philosophy. So with this example, I'm sure that you will be able to understand the basic steps involved in any of the finite element analysis. Now, I will consider another example that is pertaining to your heat transfer problem. Here, you have a composite skin which is made up of two brick layer, and in between these two brick layer, there is a insulating layer. It is as good as the insulating layer has been sandwiched between the two brick layer. Fine. You can think about that this could be a cross section of the wall of the industrial furnace, or it can be a cross section of the wall of the boiler furnace, wherein the inside temperature is very high. Fine. And the outside temperature is as good as your atmospheric temperature. And I want to know the temperature distribution as you move from the inner surface of the wall to the outer surface of the wall. Fine. So I have converted that actual problem into a one-dimensional problem. This will be obviously an approximation of the actual physics, but I have done it so that I can have some hands-on information quickly. Otherwise, you have to do a complicated three-dimensional modeling. Okay, so it is as good as here also you have some temperature that is known to you. Obviously, it's a temperature of the extreme left face, and 20 degrees centigrade that I am assuming is the temperature of the extreme right face. And I want to know the temperature distribution as I am moving from either right to left or left to right. It doesn't make any difference. Okay, for this problem, the heat is transferred via conduction. So my governing differential equation for this problem is obviously minus d by dx of your A K into dt by dx, that is equal to 0. So if you compare this one with our standard model value problem, then this product will become A and this T will become your small u. That is the only change I have to make. So let's go into the solution procedure. So I am considering three elements. Fine. Why I have to consider three elements? I cannot do this analysis with two elements. The reason is that for every change in geometrical parameter, every change in material property, you have to consider at least one element. If you recall our discussion for the previous example, we have considered two elements even though the material property is constant. The reason is that there is a change in the geometrical shape as you move from step 1 to step 2. So for every step I have considered one element. Here when you move from brick to insulation and insulation to brick, there is a change in material property. So whenever you have a change in material property or the change in geometrical property, you have to consider at least one element. So here there is a three different type of thermal conductivity or a material. You have to consider at least three elements. So for every layer I have considered three element, sorry, one element, at least one element, and this I am numbering as element 1, element 2 and element 3. And when you make an assembly of these three elements, it represents your overall FEA model. So this assembly is giving you the overall FEA model. And in your overall FEA model, you have a three subdomain. That is first one, second one, and third one. And the number of nodes you have in your global FEA model is 1, 2, 3, and 4. So these are the global FEA nodes, while this 1, 2, and 3, which are written in a circle, is nothing but your element number. So now elemental representation. So for every element, I have done the elemental representation. For brick, I am saying it's a subdomain 1. For insulation, I am considering subdomain 2. For brick, I am once again considering element 3 or a subdomain 3. And for first layer, I am considering element 1. For second layer, I have element 2. For the third layer, I have the element 3. And using the subscript and superscript notation, I have written the temperature value for local node 1 as well as for local node 2 of the element 1. In the same way, I have done for element 2 also and for element 3 also. You can see the interaction between the subdomain and the surrounding or between subdomain 1 and subdomain 2. This Q11 is as good as the interaction between your subdomain 1 and the rest of the world which is present on the left side, while this Q12 is nothing but the interaction between your subdomain 1 and 2. So the secondary variable always represents the interaction communication between either two subdomain or between the subdomain and the rest of the world. So exactly below each and every layer, I have represented the respective element notation for the primary variable and the notation for the secondary variable with respect to a local node number of that element. Okay, then once you have this kind of elemental representation, obviously you have to write the elemental relationship in a matrix form. Here also the pattern is same. Fine, but there is a change in terms of A. You can say that this is now the product of cross-sectional area into a thermal conductivity. In a structural problem, it is a product of cross-sectional area into modulus of elasticity, because there is a change in the nature of differential equation. Okay, following the same pattern, you have to write it for the second element as well as for the third element also. Once you have the elemental relationship for the each and every element, you have to prepare a global matrix. Yeah, fine. So write separately the elemental relationship for the first element, for the second element, and for the third element. While writing, what you have to do, you have to replace this primary variable notation in terms of a global notation. Please observe carefully. Fine, but still secondary variables are retained in terms of the local notation. They have not been replaced with the help of a global notation. They still have the superscript as well as they have the subscript. So this care you have to take. And as there are total 4 global nodes, as this is a one-dimensional problem, the size of the global matrix will be 4 by 4. So I have first prepare a square matrix of a size 4 by 4, that is multiplied by the value T1, T2, T3, T4, and then I am writing that is equal to some secondary variable. So first I am finding out the information about the entries that will come at the intersection of the first row, first column. So this is your first row, first column of the global matrix. From where this will come? This will come from the intersection at the elemental relationship. So in elemental relationship, here you have a first row, here you have a first column and first row. So at that intersection, whatever is the entry, that entry you have to write over here. Then for the second column and first row, this is the entry. So that I am writing. At the third column, first row, there is no entry, so I am writing 0. At fourth column and first row, there is no entry, so I am writing 0. So in this way, from the respective elemental matrix, the entries have to be identified and that has to be added to a global relationship. So once you prepare a global relationship, fine. You have 4 primary variables, that is T1, T2, T3, T4, which are unknown, as well as you have the 4 secondary variables which are not known yet. And this matrix relation is presenting only 4 equations. So at the moment, I can solve only 4 unknown. That means out of this 8 unknown, I have to obtain the information about at least 4 variables. If you carefully refer to the physics of the problem, then you can say that the T1, okay, the T1 is given to you, that is 200, T4 is also given to you, that is 20 degrees centigrade. That means the information about T1 and T4 is known to me. Fine. Now Q1, you have no idea. And Q4 also you have no idea. That is the amount of heat that is entering, the heat that is leaving. Okay. Now, can I decide something about Q2 and Q3? What this Q2 and Q3 represents? These are the localized value of a heat source at node 2 and node 3. In a present case, you don't have any localized source of heat at node 2 and node 3. In those circumstances, you can safely assume that this is equal to 0, this is also equal to 0. So now, with this discussion, we have derived information about 2 primary variables, that is T1 and T4, as well as information about the 2 secondary variables, that is Q2 and Q3, and both are having the value that is 0. So now we will substitute this one. Yeah, there is some overlapping. You can see that T1 I am substituting 200, T4 I am substituting 20, and the Q2 and Q3 I am substituting 0. So now this once again becomes a well-posed problem because the number of unknowns are 4 and the equation is also 4. You have to solve this set of equation to obtain the information about T2, T3, Q1 and Q4. And if you solve it, you will have the information about the temperature, that is T2, temperature, that is T3, and Q1 and Q4. And these values are listed over here. I am not going into the details of how you can solve it. It's a simple mathematical procedure that you have to follow. You will get the solution. Fine. So in this way, you can solve the thermal problems also. Now, this is a very good problem in terms of understanding many things. I am reading problem statement. It's a flat plate uranium fuel element for a nuclear reactor having a thickness of 6 mm and it is clad on each side with aluminum sheet of having thickness 2 mm. The rate of heat generation within the uranium material is given as 5.6 into 10 raised to 8 watt per cubic meter, and the coolant which is present on both the side of the aluminum cladding is having the average temperature of 140 degrees centigrade, and the convective heat transfer coefficient is also given, that is 2.85 into 10 raised to 4 watt per meter Kelvin. Sorry, it's meter square Kelvin. It's not meter Kelvin, it's the meter square Kelvin. And then the thermal conductivity of uranium and aluminum is also given. So uranium is having 24.5 watt per meter Kelvin, and the thermal conductivity of aluminum is 200 watt per meter Kelvin. So this is the physics of the problem, and in terms of the sketches or in terms of the schematic diagram, the same physics has been represented exactly below. If you see carefully, then this central portion is the portion which is representing the uranium material. And this is having the thickness of 6 mm. Even though it is represented on an exaggerated scale, the thickness is only 6 mm. Here, there is a generation of heat also, because uranium is highly radioactive material, and because of that, there is a generation of heat. On both the side, you have a aluminum cladding. This aluminum is having a thickness of 2 mm. Fine. And outside the aluminum cladding, there is a coolant flow, and it is flowing at the average temperature of 140 degrees centigrade, and with average convective heat transfer coefficient, that is 2.85 into 10 raised to 4 watt per meter square Kelvin. Now, if you recall our discussion, then I have to consider at least one element for the first aluminum layer, then the second element for the uranium material, and the third for the once again aluminum. That is, this is supposed to be my first domain, this is supposed to be a second subdomain, and this is supposed to be a third subdomain. So I am referring that as element 1, element 2, and element 3. But if I carefully study the physics of this problem, I don't have to consider 3 elements, because the problem is having a symmetry. That means with respect to the line or the axis that is passing through the mid of the uranium material, the physics is symmetrical. That means whatever is the physics that is present on the right hand side of this axis of symmetry, the same physics is available on the left side of the domain. As the geometry is symmetrical with respect to the axis passing through the mid of domain, as well as the physics is also symmetrical, you can take an advantage of the symmetry of the problem. Suppose if I change this temperature to 150 degrees centigrade, then you cannot take an advantage of the symmetry of the problem, because truly speaking, the problem is not symmetrical. Even though geometry is symmetrical, the physics is not symmetrical, and this will deviate that the problem is not symmetrical. So the symmetry has to be enjoyed only when the boundary conditions are symmetrical, as well as the geometry of the domain is symmetrical. Otherwise, you have to do the modeling of the whole domain. But in a present problem, we are lucky enough that the geometry is symmetrical as well as the physics is also symmetrical. We have to consider only half of the portion for the analysis. So now I am considering only the right portion of the geometry, starting from the mid of the uranium material to the end of the aluminum cladding for the purpose of analysis. And there is a change in the material, there is a change in the physics also. Fine. I have to consider at least one element for the uranium part and one material for the aluminum part. So I am saying that I have element 1 in a uranium which is starting from 0 and ending at 3 mm. And then for aluminum, I am considering the element 2 which is starting at 3 mm and ending at 5 mm. Fine. So at the axis of symmetry, I have a global node 1. At the interface of uranium and aluminum, I have a global node 2. And at the interface of the aluminum and coolant, I have a global node 3. So this becomes my FEA model. Fine. So this becomes my global FEA model. Okay. Then I have to represent each and every element separately. In element 1, there is a heat generation. So now I cannot say that my F equal to 0. There is some heat generation. In second element, there is no heat generation. It is only the conduction of heat. Whatever is coming from left part, it is conducted to the right side. But in case of first element, that is not the case. Whatever is coming plus generated, that is given to the right side. So because of the difference in physics of the heat transfer, you will find that there is a separate governing differential equation for uranium and separate governing differential equation for the aluminum. So these two equations are separately written over here. You can identify the difference between these two. Okay, this I will not discuss. Okay, this is already discussed. Okay, once again, coming to the elemental representation for uranium and aluminum. Okay, so for uranium, you will have this kind of elemental relationship. In case of aluminum, the small q is 0. That is the only difference. Here you don't have a small q term, which is that is the only difference. Other terminology are same. Then you have to substitute values of thermal conductivity of uranium, the domain length, that is H1 and H2. Here H1 and H2 is not same, it is a different. H1 is 3 mm, H2 is 2 mm. And K1, K of uranium and K of aluminum is also different. So before you make an assembly, you have to calculate the value of all this ratio or a product. Okay, so if you substitute all this material information as well as the geometrical information, you will have the elemental relationship for the first as well as you have the elemental relationship for the second one. And then by combining two, by following the philosophy and the procedure that we have discussed, you have to prepare the global matrix. That is this one. Fine. I hope you will be able to prepare the global matrix by following the procedure that we have discussed. Now, if you look at this global matrix carefully, once again you have a 3 primary variable, you have a 3 secondary variables whose values or information is not known to you. And then this global relationship is having the 3 equations only. So at the most, you can solve 3 variable. So for 3 variables, the information has to be fetched or it has to be obtained. If I go to the physics of the problem, fine, I have node 1. This node 1 is having a coincidence with the axis of symmetry. This node 2 is at the interface of the uranium and aluminum material, and this node 3 at the interface of aluminum and the coolant. Now I will ask a question one by one. Is the temperature at node 1 is known to me? No, it's not known to me, because this is the internal part of the uranium where there is a heat generation and temperature is not given to me. So T1 is not known to me. What about T2? Once again, T2 is at the interface of uranium and aluminum, and from the physics and the information that is given to me, the temperature T2 is not known to me. Then what about T3? Okay. Some students might prompt to assume this as a T3, that is T infinite as a T3, but it's a wrong information. Fine. This T infinite itself says that it is not the temperature of the surface, it is the average of temperature of the free stream temperature, sorry, It is the average temperature of a free stream. And free stream is always far away from the surface. Right. So this 140 degree centigrade is not the temperature of the aluminum surface which is having a contact with the coolant. Fine. But it is on an average the temperature of the coolant that is flowing in the vicinity of the aluminum. If you consider this aluminum surface at a 140 degree centigrade, coolant also has a 140 degree centigrade. In that case, there is no possibility of a heat transfer from the aluminum surface to the coolant because both is having the same. જોઈન્ટ થાય તો ઠીક છે. હા હા ઓકે ઓકે જોઈન્ટ થઈ ગયું હા ઓકે. Okay. So sorry for the
Sir, your voice is not audible.
Just a minute.
Yes, sir.
Hello.
Yes, sir.
Okay, fine. I think it's the last 5 minutes discussion only. Let me share the PPT. Okay. So, is the PPT or
Yes. Sir, your voice is again.
is there any issue
Yes, sir.
with the streaming of
No,
audio?
sir. Yes, no, sir. Clearly audible now.
Okay, fine. Okay, so there are some issue with the speed of internet or the internet has been dropped. Maybe because of that we were disconnected. Okay. Now only the 5 minutes discussion is there. We were discussing about the information that can be derived from the physics that has been given to you or the geometry that has been given to you. So now temperature at all the three node is not achievable, not given to you. That means the Q1, Q2 and Q3 at all the node has to be obtained. Anyhow, you don't have any option. Okay, let me discuss what we can have. This Q1 over here is as good as the things which is coming to the node 1. That is this one. Now, if I identify 2 points and these 2 points are equally located on either side of the axis, fine. I can say that, let us say this is having a notation T1 dash and this is having a notation that is T double dash. If the distance is same on either side of axis of symmetry, we can say that these two temperature values are same as it is lying on the either side of the axis of symmetry. So if that is the case, as whatever temperature distribution you have on the right side, the same temperature distribution you are going to get on the left side. What we can say that at this point, there is no exchange of information. That means nothing is coming from the left side. Fine. And it is a point that you have considered. At a point, fine, you cannot say that something has been generated. Fine. And whatever has been generated, you have taken care in terms of what? The Q. Fine. So additionally, no point heat generation is present, which is communicated to the point 1 or a global node 1. So whenever you have the axis of symmetry, you can say that the primary variables are same on the left side as well as the right side or on the either side of the axis of symmetry. And as the primary variables are having the similar values with respect to the axis of symmetry, no secondary variables are entering or it is leaving. Fine. For example, if you have the pressure which is equal on both the sides, fine, you can say that at this point, fine, the fluid element is under the stationary condition and there is no flow which is either leaving or entering the axis of symmetry. Same is the true for the temperature or thermal problem. On the both the side, if the temperature values are same with respect to the axis of symmetry, you can say that no heat is either entering or it is leaving. Fine. So if that is the case, I can say that my Q1 is 0. That means the element 1 is not receiving any heat from the outside of the world with respect to your global node 1. That is the understanding. So this discussion helps you to reduce the information Q1 equal to 0. What about Q2? Q2 is the internal node of your analysis, and until and unless the point source is present, for all internal nodes, the value of secondary variable can be straight away written as 0. That means here also you don't have any presence of a point source. Fine, that is the meaning. So for all internal node, in absence of any point source value, the secondary variable can be always thought of as a 0 value. Then what about Q3? Now this Q3 is as good as the amount of heat that is transferred from the aluminum surface to the fluid. How this is getting transferred? It is transferred via convection. So I am writing the convection equation, that is convective mode of heat transfer equation. It is H into A into difference of your surface temperature minus your surrounding fluid temperature, that is T infinite. Fine. So this is the amount of heat that is exchanged from the aluminum surface to the fluid. Okay. So I have a two direct information, that is Q1 as well as Q2, and one indirect information, that is Q3. This Q3 is obviously in terms of HA Ts minus T infinite. I will be able to write that the aluminum surface temperature is exactly equal to T3. So now Q3 has been derived in terms of T3. So if I substitute global matrix, fine, I will say that my Q1 is 0, this is not Q3, it's a Q2 is also 0, and Q3 I have written as minus H into T3 minus T infinite. Here you don't have a presence of A, it is as good as the cross-sectional area of the geometry is considered as a unit value. Fine. Then I am introducing the negative sign over here. Why I have taken negative sign? Because as per the heat transfer terminology, if the heat is entering into the domain, it is considered as a positive. If the heat is leaving the domain, it has to be considered as a negative. So to line up with that physics of the heat transfer, I have considered this as a minus H into T3 minus T infinite, where T3 is the surface temperature of aluminum and T infinite is the average temperature of the coolant that is flowing. H is the convective heat transfer coefficient. So now I have a two direct information and one indirect information that I will substitute in the global relationship. Okay, you can find the substitution of the information. This 0 stands for your Q1, this is standing for your Q2, and this one is for Q3. Fine. Then you have to do some mathematical procedure. You have to transfer this unknown value, that is this unknown, appropriately to the right hand side, so that there is a segregation between the knowns and unknowns on one side and other side. If you do that, you can find that now unknowns are only T1, T2 and T3. This is present on the left side and all known values are present on the right hand side. So this becomes the solution much more easier if you can translate all or transfer all unknowns to one side and all unknowns on other side, the solution becomes much more easier. So this form has come from the identification of the appropriate boundary condition. And once you have the separation of the unknowns and knowns on the either side, you will be having the simple form of the relationship that the 3 equation and 3 unknown. That is, this T1, T2 and T3 are the only unknown now. Fine. Rest all other parameters, numerical values are known to you. And then you have to solve this 3 equation for T1, T2 and T3. If you do that, you will get T1 is equal to 591.68, T2 is equal to 488.747 and T3 is equal to 471.947. And then if you substitute this T3 value in the equation of Q3, you will have this value. So this is the amount of heat that is being exchanged. If you carefully observe, the temperature value is reducing as you are moving from left to right. That means T1 is having the highest value, then the lowest value is T2 and the least value is T3. So this is also matching as per the physics of the problem. Heat always moves from higher temperature to a lower temperature, and finally the Q3 is absorbed by the coolant. You can see the negative sign over here, which indicates that the heat is being rejected by the solid domain to the fluid, and because of that only it is having the negative sign. So in this way, you can use your FEA philosophy to solve a simple problem, as well as once you have the understanding about the procedural aspects, you can extend it to a complex problem also. Fine. We don't have a time right now to discuss also, and you don't have a knowledge also how it can be extended to a two-dimensional problem, three-dimensional problem, and the complex nature of the domain. Fine. But once you are familiar with the fundamental and the different aspects of the finite element method, fine, with little bit of more efforts, you can extend the same procedure to either 2D problem or to the 3D problem. So with this, I would like to close the today's session. If the participant is having any question, I will be happy to answer that one.
Participants, you are unmuted. Please ask the questions.
Sir,
Yeah.
sir, if possible, kindly switch on your camera because we are taking some peaks of your lecture.
Yeah, see, the issue is that I don't have a camera installed on my desktop.
Okay, sir.
Fine,
Okay,
that is the issue.
No problem, sir. No problem.
Okay.
Hello, sir. Namaste.
Yeah.
Sir, this is Dr. Harina from MIT Manipal, sir.
Okay.
So I'm very happy. Yesterday and today also, it was very beautiful the way you have explained.
Yeah,
Sir,
thanks for the kind words.
Sir, I have two queries. This FM you were talking about, sir, that you're saying the Galerkin finite element method, no, sir. So I have seen some of the paper where they are implementing wavelet along with the Galerkin approach. Any suggestion about that, sir? Why that wavelet for Galerkin method, or will it be the best one compared to the normal Galerkin? Something. Any information about that, sir, from your end?
Truly speaking, fine. I am teaching finite element method, fine. But I am not having the research in the area of finite element method, fine. So what you are saying is the research area, fine. They are trying to make it more and more flexible. So there is a issue that some location with respect to some physics, they find it difficult to apply your Galerkin FEM method as it is.
Okay.
Fine.
Maybe the ill condition in that case.
Maybe the reason because of that they have to make a slight or a little bit change in the existing Galerkin finite element method.
In terms of basis function, I have observed they prefer the wavelet.
Yeah, that is what I am saying. Fine. I am teaching FEM, but I am not having the research area in the FEM.
Okay.
Fine.
Okay, sir. Yeah, sir. This can be.
Sir?
Hello.
Yeah.
So can I continue?
Yeah, you can continue.
Yeah, sir, for this, the elaborated way you have explained FEM, the preferred reference book will be the Reddy, sir?
Yeah,
Reddy.
it's a Reddy, Jane Reddy.
Any other books, sir?
You can refer to Fagan also.
Fagan, okay.
Fine.
Yes.
For the beginners, Fagan is a good book because it will give you the overall aspects of the finite element method. But if you are interested to know what is exactly happening behind the screen, fine. Like there are two aspects. One is the front end, another is the back end. So if
Yeah.
you are interested in knowing what is happening at the front end, I think Fagan is the good thing. But if you want to write your own code, or if you want to write a program for your own specific problem, then the Jane Reddy is the good reference book.
We can develop MATLAB programs, no, sir, through that.
Yeah, you can develop a MATLAB programs.
Yes, sir. Thank you. And last question for Modi, sir. Sir, yesterday's in that YouTube link, only the half of the session were there. We were not able to see the complete one. If
Yes,
possible, will you please send the recorded session so that we can revise and study, sir?
Yes, madam. We are recording all the sessions, and we will definitely put new links for that. And we will definitely share after completion of this STTP.
Oh, after completion. Okay.
Yes,
I
sir.
thought before the exam so that we can recall every day after the end of the day when we go. Okay.
We try, ma'am, because
Yes.
the file is too large. Full day video is recorded in MST,
Yeah.
and we are extracting that, and we'll try to share it as early as possible.
Yes. Yes. Thank you, sir. Rupesh, sir. Really, it's wonderful. Thank you very much, sir.
Yeah.
Sir, good afternoon, sir. My name is R.S. Kiran. I'm speaking from Visakhapatnam.
Yeah, please go ahead.
Sir, actually, do we have free and open source calculators for getting the solutions immediately on the spot for the problems that we have discussed now?
There is nothing like a free calculator, but you can develop these procedure in Excel sheet. Fine.
Okay.
Once you digest all this procedure, you can write systematically all these steps in Excel sheet. And in Excel sheet, there is a very good feature. The set of rows and set of column can be declared as a matrix.
Okay.
So once you declare that as a matrix, the inversion of matrix and multiplication of matrix in Excel is very easy.
Yes, sir.
So you don't have to go through the structure of any new programming language, maybe Scilab or maybe a MATLAB.
Sir.
For the elementary purpose, you can take the help of Excel also.
Okay. Yes, sir. Yeah. Thank you, sir.
Yeah.
Yes, any more questions from participants?
Yes, Rupesh sir, good afternoon. This is Dr. Varadarajalu.
Yeah.
May I audible, sir?
Yeah, you are audible, clearly audible.
Yes, sir. It was a very nice presentation from yesterday. And concerning this particular problem, we are trying to solve the temperature effects. When it was associated with the point loads, how we can solve this problem, sir? The point load, the nodes 2, 3, for instance, the nodes 2, 3 has load 100 and 200 Newton. How it can be solved, sir?
Okay, so you are referring to that first structural problem.
Yeah, along with this temperature effects. When it was associated the temperature effects as well as there is a point load, how it can be solved?
Okay. Like the stresses are introduced because of the applied forces as well as because of the thermal stresses.
Yes, sir. Yes.
Yeah, you can take it together. Only thing is that your governing differential equation needs modification appropriately.
Oh, okay.
Fine. You can take care of this one. I think you can refer Reddy or you can refer it to Fagan. In Fagan and Reddy, they have given the example of this kind of coupled physics, wherein the stresses are introduced because of the expansion or elongation because of the difference in temperature, as well as there is a point load that is existing on the structure. So the stress generation is because of the forces as well as the elongation.
Yes.
Fine. I think
Okay.
on the right, I think on the right hand side you will have an additional term that is called AE alpha delta T. It will be -1 1.
Okay, there it is. AE
Yeah.
alpha
So
delta T minus 1 for temperature
yeah,
problem.
temperature effect. Fine. So that elemental matrix will get modified.
Okay, okay, okay.
Fine. So for exact form, you please refer to the book. Don't take my words as a granted. Fine.
Fine, sir. Fine, sir.
Yeah,
Fine, sir.
yeah. But it is available. You can take care it.
Yes, sir. Thank you, Rupesh.
Yeah. Yeah, Ashish, if there are no more questions, we can close this session.
Yes, sir. Yes, sir.
Hello?
Yeah.
Sir, is I am audible?
Yeah, you are audible.
Yes, audio.
Sir, up till now we've seen that the interpolation function is of a linear order.
Yeah.
But if I take it as cubic or a quarter order,
Yeah,
is
it
that
depends.
any
See,
effect on the result?
yeah. See, it depends. See, there is a first order element, there is a second order element. Now, this first order element will give you the nature of interpolation function or a safe function that is of the first order. Fine. But if you assume that the variation of a variable over the element is having a second order, then your safe function will be quadratic in nature.
Okay.
So whether the safe function will be of a first order or the safe function will be of the second order, it depends the order of element that you have chosen. If you choose the order of element as a first order, now what is the meaning of order of element? The order of element means if the linear distribution of variable is existing over the element, the order of element is first one. If you assume that the distribution of the primary variable over the element is of the second order, then the element is referred as the second order. Fine. So it's a very simple. If you take linear distribution over the element, the safe functions will be of the linear order or of the first order. If you assume the quadratic distribution of the primary variable over the element, then the safe functions will be of the second order or they are of the quadratic nature.
Thank you, sir.
Yeah.
Any other participants? I think, sir, everybody has is clear now, and I'm very much thankful on behalf of FDP team and Mechanical Engineering Department, Government Engineering College, Bharuch. I'm very much thankful for your for sparing the valuable time for us and giving this enthusiastic lecture and being very patiently answering us. Thank you, sir.
Yeah. Thanks for giving this opportunity to interact with the young minds. Fine.
Thank
Yes,
you,
sir.
sir.
Yeah. Thank you.
Feedback link. Hello.
1 minute, sir. We are sharing feedback link. Attendance and feedback, both links are now in uh, chat box. Kindly fill attendance as well as feedback form. Yes, ma'am. हाँ मैडम. हाँ મૂકું જ છું, એ જ કરું છું, એ જ કરું છું, એ જ કરું છું.
A very good afternoon to all of you.
Good afternoon, madam.
Good afternoon, Chaitanya sir. Uh, Dear participants, we welcome back to the second session of day 2. Dr. Chaitanya Desai sir has already joined, and sir already has delivered his session yesterday in the afternoon session. Sir, I will request you to continue with the session. Thank you,
Okay,
sir.
okay. Thank you very much. Very good afternoon, all of you again.
Good afternoon.
So, yeah. So let me continue with the second session, that is finite element formulation. Before I start this session, let me recapitulate the points which we have discussed in the last session or last class. Uh, we have started the discussion with the mathematical modeling for one-dimensional spring mass system. Using Newton's second law of motion, we can derive the simple linear second-order differential equation. Based on that equation, if we have the standard solution procedure, which is called exact solution procedure for the second-order linear differential equation, we can determine the roots of the differential equation, and from that we can identify the general solution for the mathematical model. From the general solution, we can capture the unknown constants by applying certain conditions. Once the constants are determined, then it can be called as a particular solution. So this is the standard procedure in the mathematical modeling part. But as I said, in so many cases of research field or in engineering, the differential equations may not be as simple as that of a spring mass system. The differential equation may be partial differential equation of higher order, maybe linear, maybe non-linear. So sometimes we do not have the exact solution procedure. So in that case, we are going for the approximate procedures. So in the last class, we have discussed about few names about of the approximate methods, like finite difference method, finite element method, finite volume method, spectral method, mass free method likewise. And I have simply given the difference between the FDM and FEM concept. So finite difference method is generally applied on the strong form of the differential equation, while finite element method is best suited when the form a weak form or the variational form. And again, interesting point is what is the physical significance of variational form, of deriving the variational from the differential equation. And as I said, that variational form is in the form of a functional, and functional is the function of a function which is generally a scalar quantities, and scalars are always invariants. Invariance means it is independent of the coordinate system, hence its formulation is very simple compared to the vectorial quantity and the tensorial quantity. That is why this variational formulation is important. After that, we have discussed about the integral formulation of the governing differential equation, and in the integral formulation we have to use the integration by parts formula. So while using the integral formulation, the very first step is to multiply the entire differential equation with some weight function and integrate it over the whole domain. Please listen it carefully. We have to integrate the entire integrand over the whole domain rather than a subdomain, which will be the part of this FE formulation. So when you apply the integration by parts formula, the order of derivative will be reduced. Like second order derivative for the dependent variable will be converted into the first order derivative of the dependent variable, and the first order will be transferred to the weight function. So that is why it is called weak formulation, and based on the weak formulation we can have certain mathematical or approximate methods like Reed's method, Galerkin method, Petro-Galerkin method, collocation method, and least square methods. I have only explained Reed's method because the methodology might be similar convergence, the iterations might be slightly different, but ultimately we are going to use the Ritz-Gallagher method in the FE formulation. That's why only Ritz method was discussed. Now in the finite element formulation, the concepts which we have discussed in the last session will be directly applicable. So this is the very interesting formulation for the governing differential equation. Before that, as I said even in the last class, generally in the research field we are using ready-made softwares for solving the physical system using finite element method like ANSYS, Abacus, or many more. And in some cases, if we are doing the hardcore research, if we can derive the mathematical model, we can even use the finite element formulation and write our own code in Fortran language, and we can solve the problem. But one important part as far as the formulation is concerned is the selection of a shape function and all these weight function kind of things. So in this particular session we are going to discuss the important ingredients of finite element formulation if we are having a differential equation in our hand. So again, I'm assuming the one-dimensional second order ordinary linear differential equation, which we will be solving using finite element method. So first of all, let me again take the model boundary value problem. This is the same example I am taking again, minus d dx. Again, please listen carefully. I am reading this equation like this, minus d dx. It is not minus d by dx. So minus d dx into the bracket a du dx plus some constant c into u as a function of x minus f of x is equal to 0. So by looking to this equation, we can say that the dependent variable of this equation is u, while the independent variable is only one, that is x. Hence it is ordinary differential equation. And if in this case, suppose if a is constant, then you can take it out of this integral sign, and this equation will become d square u dx square. So maximum order of this differential equation is second. Hence it is called second order differential equation. A, C and F are constants, or it may be a function of x if it is not a function of u even. Hence it is called a linear differential equation, and this is called the boundary of the differential equation. Boundary of the domain, you can say that. X is the space variable, its lower limit is 0. You can even write less than or equal to and less than or equal to L. This equation is subjected to certain boundary conditions. The first boundary condition is specified as u at x is equal to 0 is equal to u0. Even this equation, this kind of condition was discussed in the last session, that if the dependent variable is specified at certain location, then it is called a geometric or kinematic or Dirichlet boundary condition. Geometric, kinematic or Dirichlet boundary condition. In the second case, what is defined? You can see it is the derivative of u. It is called a gradient of u. So a into du dx at x is equal to L. It means if you are talking about the 1D problem like this, let us say bar problem. If I assume that x is equal to 0 here, x is equal to 0 and x is equal to L here. So the force and Newman condition is specified at this point, while at this location I am applying the kinematic condition. So this is the interpretation of this model differential equation. So you can say that the given differential equation is having one-dimensional spatial coordinate x, where two boundary conditions are specified, and one condition is called geometric or kinematic or Dirichlet condition, and the second condition is called as a force condition or Newman condition because the derivative is specified. Examples are many more. In the last last lecture, even I have given the complete table. Only one example from that I have included in this case. Okay, suppose the same equation. Why it is called model boundary value problem? Because the same governing differential equation can be used to represent many field of the engineering. Suppose in the case of a solid mechanics, if I'm talking about the bar, and if we want to find out the longitudinal displacement of the bar, then if you replace this coefficient A by axial rigidity EA, C may be 0, maybe some constant, and the distributed force F is given to you, and the secondary variable is some force, like this problem I'm talking about. If you want to calculate this displacement of this bar when it is subjected to some force at this end and this boundary is fixed, this kind of problem is represented by the given differential equation. And if assume that the body forces are distributed or tractions are distributed along the length of this bar, so this problem can be highly be predicted using this governing differential equation. That is why it is called model boundary value problem. Only thing is you have to replace these quantities by certain values. Okay, so first step in the FEM. So yesterday in the second session, I have given a simple example of the steps followed in the finite element method by capturing the perimeter of a circle. What we have done, we have divided the circle into n number of line segments. In the first case, I have taken 5 lines and mapped the circle using pentagon. But looking to the geometry, we can say that it is having a huge error. So after that, we can remove one element. That element equation can be derived. Again, that element can be put at the original location at the nodes, and we can determine the total length of this line element. So in that case, we can calculate the total length of all these line segments, and if this answer is equal to 2 pi r, we can say that the approximate value is exactly matched with the final value, that is 2 pi r. But if it is not, then we have some error. That error must be minimized. So how we can minimize the error? We can reduce the length of the element. In that sense, we are increasing the number of elements. So these are the standard procedure followed in the finite element method. So the same steps I am following again. We are discretizing the domain. Look at here. I am talking about the one-dimensional problem. So this is the total length of the bar. I am fixing my coordinate system at the left hand side where x is equal to 0 here and x is positive in this direction, and the outermost point, that is x is equal to L, that is a final domain. So the discretization of domain means you have to divide this element into n number of small subdomain. So you can see the second figure here where I am giving the number of one-dimensional elements where the first node is located at x is equal to 0. And the total length of the first element is x1 to x2. This is the second node. You can see 1, 2, 3, 4 up to n number of elements I have used to model the simple bar where the elements are connected at the nodes. This is called node, this is called node, this is called node, and this is called element. One element, second element. So you can see element number 1 and element number 2 is connected at a common node. So that is why here the dependent variable should be continuous, and that is why continuity requirement will be satisfied, should be satisfied while solving the finite element analysis. I am assuming the certain node here, this is element. Suppose point A and point B I am selecting randomly. So notation wise I am using length of the element is HE. Assume that A point is located at x is equal to xa, and this node must be xe plus 1. If xe is the dimensions of a node, then this must be xe plus 1, that is equal to xb. So mathematically or geometrically I can say that xb minus xa will be equal to the length of the element he. So this is the discretization step. Now what are the convergence and how the convergence of the results are guaranteed? So there are 3 approaches. First is called H refinement. H refinement means why I am using small h, because H stands for the length of the element. H refinement means you can divide this entire domain into subdomain by selecting the length of the element. In this case, if I select the smaller line segment, like first one, second one, third one, fourth one, fifth one, likewise, it means I am reducing the length. It is called H refinement process. So this is one of the approach or one of the method to find out the convergence of the result, which is called H refinement. Second is called P refinement. P refinement means order of polynomial, which is used to find out the dependent variable in one element can be improved by selecting 2 nodes, then 3 nodes in element, then 4 nodes in element, then 5 nodes in a single element. It means I am increasing the number of nodes within the element. That is called P refinement by keeping H constant. Very, very interesting. You should keep H as it is and increase the number of nodes from linear to quadratic, from quadratic to fourth order, from fifth order likewise. This is called P refinement. This is one of the approach. And the third is called HP refinement, that is mixed refinement. Depending upon the criticality of the problem, you have to select certain small size of element along with the higher order polynomial to capture the field variable. So third is very interesting, and generally in critical component you have to use this HP refinement even. So in the first step, even honestly saying, it is based on the judgment, it is based on the experience of the analyzer who is using finite element method for solving the real life problem, that up to which level you can afford the H refinement or P refinement or HP refinement. This is the first step, that is called discretization of domain. I'm hoping that the picture is visible and the concept is clear. First step of the finite element analysis, where we can divide the total length of the domain into number of small segments. Second step is the derivation of elemental equation. For deriving equation, it involves 3 steps. In the second step, we have to follow 3 more steps to get the final elemental equation. The first step is to construct the weighted residual or weak form of the governing differential equation. That is why yesterday I have discussed the different methodology of solving the governing differential equation by converting it into the weak form. So the first step is to construct the weighted residual or weak form of the governing differential equation. Second, assume the form of approximate solution over a typical finite element. It means we have to derive the approximate solution for a particular element rather than the entire domain. That is why the difference between the integral formulation and the finite element method. Different methods which we are using, that is called variational methods like Ritz method, Galerkin method, Petrov-Galerkin method or collocation method. Those methods are directly used over the entire domain. Here these methods are applied for a particular element. That is why it is called finite element variational formulation. So assume the form of the approximate solution over a typical finite element. And the third step is derive the finite element equations using approximate solution. The approximate solutions which we have assumed in step number 2, we have to use it in the third step and derive the finite element equations. So one by one we are going to follow these steps and we are going to derive the finite element equation. So again I'm repeating, in the very first step what we have done, we have discretized the domain into subdomains. In the second step what we have done, we have to derive the elemental equation, and for deriving the elemental equations we are going to follow 3 steps or 3 procedures. First is we are going to construct the weighted residual or weak form. Second, we will be assuming the approximate solution over a typical finite element only. It means only one element. And then we are going to derive the finite element equations using the approximate solution. So for that, let me again take the same mesh size. Again assuming that the mesh size is uniform. Uniform mesh size means the length of each element will be same. Here, all these lengths will be same. And I'm assuming certain element domain is represented by omega I and its values xa and xb. Assume that this is xa and this is xb likewise. See here, this is xb, and I am removing this element for deriving the elemental equation. So typical element is removed from this figure and it is drawn here again. This particular point is the first node where I am keeping my global coordinate system. Very, very interesting. There are 2 coordinate systems which I am going to use. First is called global coordinate system and the second is called local coordinate system. So globally it means when the coordinate system is defined at node number 1, this particular node, I am talking about this node is located at x is equal to xa. because its first limit is xa, and the second node of this particular element is located at x is equal to xb. So you can say x is equal to xb is the second limit. So you can have xa and xb. So geometrically, if I subtract xb and xa, means xb minus xa, what I'll get? I'll get he. This dotted line indicates that I have removed only one element from the mass. So these elements I'm not considering right now, but the elements are there. Now the second coordinate system is always attached at the first node of a particular element, always, or the first node of the particular element. So I'm attaching the local coordinate at this particular point, where the notation is x bar rather than x. X belongs to the global coordinate system and x bar is for local coordinate system. So x bar is always 0 at the first node, and x bar will be equal to he, because he is the total length of the element. So I mean to say that local coordinate system integration value is always 0 to he, 0 to he, 0 to he, while globally integration limit is always changing. In the first case it is equal to xa is a lower limit, in the second case xb is the higher limit. If I select this element, then xa and xb value will be different, because it is measured with respect to the origin here, and origin is located here. So integration wise, this will take a little more time to integrate the functional value here. When we are using the global local coordinate, the integration limit is always fixed 0 to he, and even in the coding this is very easy to implement. So this is the notation which I am going to use. Now if I select this particular element again, and if I identify the primary and secondary variable, now you can see for this given differential equation, u was a dependent variable. So what are the boundary conditions here? U at x is equal to a, means when x is equal to xa, means at this particular point I am assuming that its value is equal to u1. Its value is equal to u1 because it is node number 1 for a particular element, and this is the second node where the dependent variable u or primary variable u at x is equal to xb, its value is u2. u1 and u2 may be any value, but for the particular notation I am saying that it is equal to u1 and this is equal to u2. As far as secondary variable is concerned, the outward normal vector for second number node is in this direction, and here the outward normal vector for this first node is in the outward this direction. So this direction and this direction are different, they are opposite. That is why I am using minus sign, minus a du dx at x is equal to xa, and here a du dx at x is equal to xb. So this is called implementing a primary and secondary variable at node number 1 and at node number 2, and this particular q as a function of x I am defining in a different field application. These values are different. This may be represented as a body force vector or traction vector. Likewise, depending upon the different field applications, this value might be different. And again, say at node number 1 I am attaching the local coordinate system x bar. So this is the sign convention I will be using for deriving the elemental equation. Now the next point is the weak form or and minimum quadratic functional. See, when we are deriving the weak form, yesterday I have discussed the importance and the importance of the weak form from the governing differential equation. What is the difference between the weak form and the weighted integral form? Again, recall the concept. In the case of weighted integral form, what I am doing, I am integrating the entire differential equation, let us say r as a function of x, and I am multiplying with some weight function w, and I am putting it equal to 0. This is called integral statement. But in the weak form, what I am doing, I am using integration by parts here. I am using integration by parts, and then after using integration by parts, the final form I am getting includes even the boundary condition. In the boundary conditions, two kinds of possibilities are there. One is called essential boundary condition, and the second is called natural boundary condition. So in the case of weak formulation, natural boundary condition is already modeled. So only essential boundary condition needs to be satisfied, which I will be discussing in this statement even. So let me go through it. As I said, once you remove the element, you have to determine or assume the approximate solution. Let me go through it here. Look at here. Assume the form of approximate solution over a typical finite element. Let me assume the form. The form is assumed as summation of j is equal to 1 to n uje psi je into x as a function of x. Okay. When you are using different books, reference books for finite element method, notations might be different, to be honest. Sometimes people are using n letter, sometimes people are using capital or phi letter. I am using psi. So E stands for upper superscript, which I am using in this case is for element, and this index is the total number of nodes, you can say that. So uj psi j is a function of x. Look at here, this is not a constant, it is a function of x. So this is the approximate polynomial I am using. It is called a polynomial solution over a typical finite element. It is assumed in this form. So the coefficient UJs are determined such that the model equation is satisfied in a weighted integral sense. Now, what I am doing here, I am using the first step of the integral formulation. So I am multiplying the entire differential equation with a weight function and integrated over the elemental length. Look at here, lower limit is xa, upper limit is xb. Yesterday when we have solved this kind of equation, my limit was 0 and upper limit was L. But instead of 0 to L, now I am using XA and XB because we are applying this integral formulation for a particular finite element. That is why it is called finite element wise variational formulation. So W is a weight function multiplied by this entire differential equation, integrate over the particular length element is equal to 0. So this is called weight function. When W weight function is assumed as psi, where this psi I am talking about, if W is equal to psi, the resulting finite element model is called as Galerkin finite element model. Unfortunately, yesterday I could not discuss the Galerkin method. Only I have discussed about the Reed's method. Reed's method is having two constants, Reed's constant plus some phi function which needs to be guessed, and while guessing the phi function we have to follow certain conditions. In the same way, when we assume W is exactly equal to this psi, the resulting finite element model is called as Galerkin finite element model. Please remember that. Now using integration by parts, again I am saying I have given 3 formulas for the integration by parts in the last class. I'm very sorry that it is very difficult to remember everything from the last class, but at least you can recall that the okay, formula was there. So using that formula, if you apply it to this given integral form, then you can have this final form. Integration of xa to xb, a dw dx du dx plus c uw minus wx, or you can say omega x, into dx minus boundary term. Look at here. The first term, when you look at in the original differential equation, the order was 2. It was d square u dx square term. After using the integration by parts formula, the order of differentiation is reduced by 1. At the same time, this order is transferred to the weight function W1, and hence I am saying that the continuity requirement for this u function is slightly reduced by order 1 plus cuw minus wf dx, and this integration by parts, when you apply it, automatically includes the natural boundary condition. You can say when I have given the differential model boundary value problem, it was having this boundary condition which is called forced boundary condition or Newman boundary condition, and this is even called as natural boundary condition. So the limit is xa to xb, w into a du dx lower limit is xa, upper limit is xb, and that is equal to 0. Now, identify the primary and secondary variable. Because this is a model boundary value problem, you have to identify the primary and secondary variable. Since this is a simple problem, but if sometimes when the problem is of fourth order differential equation, like in the case of Euler-Bernoulli beam, governing differential equation of Euler-Bernoulli beam is fourth order differential equation. In that case, you will be getting two terms in the boundaries, one which is having w and the second is having dw dx term. So in that case, identification of primary secondary variable is important along with its physical significance. So for identifying the primary and secondary variable, you have to only concentrate on this boundary term rather than this integral term. Forget about this right now. Only concentrate on the boundary term. As I said, when you look at the boundary, the exact form of the weight function will be equal to the primary variable, because primary variable, and this primary variable in this case is w. So w represents the u, hence the primary variable is u, while the coefficient of this w is equal to the secondary variable. So for looking to the boundary, w is coming in an exact sense, not its derivative, hence only one primary variable is there, that is equal to u, and secondary variable is a du dx, and that is equal to q, which I am calling it is some force value or q value, or it is even called as secondary variable. So primary variable, when the boundary conditions are specified on the primary variable, then it is called essential boundary condition, and when the boundary conditions are specified for the secondary variable, then it is called a natural boundary condition. So now let us apply the boundary conditions. We know that when x is equal to a, I have given u is equal to u1. Again I am saying it is for a particular element e, and when x is equal to b, u will be equal to u2. So I am talking about this line element. First node, this is the second node. Here it was u1 in the discretization, and here it was u2 in the discretization. Sorry, it is very difficult to write in the direct PowerPoint, but believe that this is equal to u2. Let me write it again, u2, and here you can have q1, and here you can, which was already there in the previous slide, but for your ready reference I am redrawing it again. So uh, that is for a particular element at x is equal to a, its value is u1, at x is equal to b, here its value is u2. This is called essential boundary condition. Second case is, here it is minus because outward normal vector is in this direction. So minus a du dx at x is equal to a is q1e, and a du dx at x is equal to b is q2e. These two are the force boundary condition, and these two are the essential boundary condition. When you look at the weak formulation here, when you look at the weak formulation here, at this particular point you can say this term is already included. It means natural boundary condition is already included in the weak formulation. So let us apply this boundary condition in the weak form. Here, look at here. When you apply the upper limit minus lower limit, means w at x is equal to b, a du dx at x is equal to b, minus w at x is equal to a du dx at x is equal to a. It is simple substitution of the upper limit minus lower limit. With this sign convention, you can write this simple form, minus wxa q1 minus wxb q2 is equal to 0. None of these values are 0. Very interesting, because this element is selected from interior nodes or interior region of the entire domain. So what is happening at this point and at this point, it is unknown. We cannot say it is 0. It is not specified. In the previous case, when we are integrating over the whole domain, then if the forces are applied at the end, we can directly substitute the values of q's according to the given conditions, according to the given values. So using these conditions, we can have this weak form, a dw dx du dx plus c uw minus wf dx. This is the lower limit, this is the upper limit according to the sign convention. So the resulting finite element model is termed as weak form Galerkin finite element model. The resulting finite element model is termed as weak form Galerkin finite element model. The weak form contains two types of expressions. Look at this particular equation again. This entire equation contains two types of expressions, those containing both W and U. Look at here. Let me select this highlight again. This term, first term, entire term, it includes W and U. Second term, it includes U and W both. This term includes only W. This term includes only W. This term includes only W. So the weak form contains two types of expressions, those containing both W and U, which is called bilinear form, and those containing only W, that is called linear form. So let me identify it and write it as BWE, that is called bilinear functional form, integrated over the whole domain of the element, that is XA to XB, A dW dx, du dx plus CUW into dx. This is the bilinear functional form from the derived weak form of the governing differential equation. Similarly, I can derive the linear form, that will be having three terms. One is this one, second is this one, third is this one. So it is written separately. W f dx, only one W is there here. Look at here, second W is here, third W is here. So three terms are included in a linear form and two terms are included in the bilinear form, because using the variational formulation from the weak form we can directly write the finite element equation. Now from this, the entire weak form, it means I'm talking about this expression. If you open this bracket and if you remove this term outside, if you take this term outside, and if these three terms are shifted to the right hand side, then the left hand side will be equal to B and the right hand side will be equal to L. That is what is written here. The weak form can be expressed as BWU is equal to LW, and this is called the variational problem. This is called the variational problem. The functional can be determined as, yesterday I have defined the functional from this, I as a function of U, that is equal to 1/2 BUU minus LE, that is a quadratic form. So when you replace W by U in this equation of B, you will get this functional form. IU will be equal to 1/2 integration of XA to XB. Now I am replacing W by U, that is why it is called du dx whole square. Similarly, everywhere you can say W is removed and it is replaced by U. In solid mechanics, if you talk about the design field, solid mechanics field, this IU is having its own physical interpretation and it is called a potential energy. And as I said, in the case of variational form, it is having a functional form, and functionals are always scalars and scalars are always invariants independent of the coordinate system. Again I am repeating. And see, answer is a potential energy. Energy is always a scalar quantity. So this can be directly added. Conservation of energy principle, you can say that. So in solid mechanics, IU is called the potential energy. So you can have the physics while using the mathematics of solving the given differential equations. The relationship between the weak form and the minimum of quadratic function is del I will be equal to 0. If you again use the variational calculus, you can have the original differential equation, and that is called the principle of minimum total potential energy. This is known as the principle of minimum total potential energy. So from the weak form we can derive the principle of virtual work even. Now let us use this weak form again and go with the second step of the second stage, that is approximate solution. The weak form over an element is equivalent to the differential equation and natural boundary condition. Again I am repeating, the weak form over an element is equivalent to the differential equation and the natural boundary condition, because it is derived based on the integration by parts. Hence the approximate solution UH is required to satisfy only the essential boundary condition, because it is not modeled by the integration by parts formula. So when we are using the approximate solution, Again, be careful. It has to be satisfied. Means essential boundary conditions has to be satisfied for the solution. So conditions for approximate solution. How to predict it? You cannot directly guess the approximate solution randomly. Otherwise, your solution may not be converged. Certain conditions should be satisfied. First condition is it should be continuous over the element and differentiable as required by the weak form. Interesting. It should be continuous over the element and differentiable as required by the weak form. Again, let me take this particular element, element 1, element 2, element 3. So you can say element 1, element 2 and element 3. All these three elements are connected by the node. This is node, this is node. So at this particular node, second number node of the first element and the first number node of the second element, they are connected. So here u should be continuous. Dependent variable, primary variable should be continuous. It cannot be discontinuous, and it should be differentiable as required by the weak form. Look at the weak form, where it is here. Look at the weak form. Here, weak form is having only one order differential term, du dx. So minimum requirement means if I guess u is equal to some value, let us say 1, then it is not valid. Why? Because when you differentiate, this term will be 0. It is not x. If I use only x, then answer is yes. U is differentiable, but constant is missing. So what are the conditions for guessing the approximate solution? First condition is it should be continuous over the element and differentiable as required by the weak form. Second is it should be a complete polynomial, means it includes all lower order terms up to the highest order used. Highest order for this particular case is 1 only, because only first order differentiation should be there. We do not care about the second order, because second order differentiation may be there, may not be. It may be continuous, it may be discontinuous. We do not have to impose certain condition on the second order derivative. And the third is it should be interpolant of the primary variable at the nodes of the finite element. It means interpolation should be there. These three conditions should be satisfied for properly guessing the approximate function. It should be continuous over the element and differentiable as required by the weak form. It should be a complete polynomial. You cannot directly guess x to x squared plus x to 5 likewise. And it should be interpolant of the primary variables at the nodes of the finite element. So for this case, the weak form, the minimum polynomial order is linear, because we are having only first order differential term, that is du dx, in the weak formulation. Hence linear polynomial is sufficient. A complete linear polynomial is of this form. I am calling c1 and c2 as some random constants, but this is the constant term and this is a function of x, or c2 is constant but it is multiplied with the linear term x. So you can say it is the first linear polynomial. So this is the guess value for the given differential equation, because it contains only first order derivative of u. So I am assuming that this is the approximate solution, c1e plus c2e x. My job is to get the value of c1 and c2 after the application of essential boundary condition. Now look at here. What are the essential boundary conditions? We know that when x is equal to a, your u will be equal to u1. When x is equal to b, your u will be equal to u2. So I am putting the value of x is equal to xa. When I put x is equal to xa, I have to write u1 here. When I substitute x is equal to xb, I have to write u2 here. A superscript indicates element. So I am writing everything for a single element only. It is not for the all elements. But okay. So if the mass is uniform, it may be uniform for all the cases. But right now, believe me that this is the elemental equation we are deriving. So c1e plus c2e. So again say these are the two equations and two unknowns. Can we solve? Yes, we can solve, and we can have the exact solution even. So these equations can be written in a matrix form: u1e u2e is equal to 1 xa 1 xb into c1e c2e. So to get rid of c1 and c2e, this matrix should be inverted. and you can have the values of C1 and C2 in this form. 1 upon He U1 XB minus U2 XA, and C2 will be equal to 1 upon He U2 minus U1. So two constant values are determined by application of essential boundary conditions. Again, I'm repeating, you do not have to worry about the natural boundary conditions because it is already modeled in a weak formulation. So the constants are only calculated after the application of essential boundary condition. Now once it is did out, see here, same element is written again. This point is XA, this point is XB, this node is 1, this node is 2. In the global coordinate, these equations are written in a global coordinate because XB and XA is there. Otherwise, you can have the same equation for the local coordinate even. Here, local coordinate means x bar coordinate. For node number 1, the coordinates are attached at this node only. Hence, x bar is equal to 0. For node number 2, the maximum length of the element I am writing is HE. Hence, x bar is equal to HE. For any particular value of x bar, at this particular value of x bar, which I am calling it is equal to x minus xa. This is called x. This term I am calling it x. For any interior point I am talking about, x bar can be calculated as x minus xa, and hb is equal to xb minus xa. So if I replace this equation in terms of this local coordinate, it is possible. So now we know that u is written as c1 plus c2x because it is a linear polynomial. We have assumed that according to the highest order derivative in the weak form. So UH is equal to C1 plus C2x. Well, now if I'm substituting the value of C1 and C2, you will be getting this equation. 1 upon He U1 XB minus U2 XA plus X upon He U2 minus U1. Still this is in the form of global coordinate. So this can be written as Psi1 U1 plus Psi2 U2. As simple as that. Where this Psi1 U1 and Psi2 U2 can be written in indical form. This is called indical form. J is equal to 1 to 2 because we are having only two nodes here. So UH is equal to Psi j into Uj, where Psi1 and Psi2 can be written in this X form, and it is equal to XB minus X divided by XB minus XA, X minus XA divided by XB minus XA. These are called the values of Psi, and it is a function of X. Look at here. What is the beauty in this particular functions? If I substitute x is equal to a, xa, what will happen? This is xb minus xa, this is xb minus xa, it will be cancelled and you will get 1. So psi1 at x is equal to xa, its value is equal to 1. When I substitute x is equal to xb here, this will be 0 and you will get 0. So psi1 at x is equal to b, its value is 0. So its value varies from node number 1 to node number 2 linearly. It is having a slope. So you can have the idea that this is a linear shape function or approximate function. Xb minus xa, x divided by x. And this difference is what? It is equal to he. This is the length of the element. So which are called the linear finite element approximate functions, or it is even called as shape functions. If you refer different books, again as I am saying, then these notations are n1 and 2. Sometimes it is phi1 phi2. Again I am saying I am following different reference books. That is why these notations are psi1 psi2. But you must know that it is a functions, approximate functions, and that too linear approximate functions, or it is even called as a shape function. Hence this guessing is in the form of u1 psi1 plus u2 psi2, uh is equal to. What are the properties? Look at here. Psi I at a particular point xj is equal to 0 if I is not equal to j. If I is not equal to j means what? If I am talking about node number 1 here, node number 2 here. If I is not equal to j means I am talking about this node. So if x is equal to xa, and then this xb minus xa and this xb minus xa will be cancelled. So this particular point is having 1 and this value will be 0 in this case. Next here it is 1 and here it is 0 for side 2. So if I is equal to j, I can say this is equal to 1, and if I is not equal to j means at node number 2 its value is equal to 0. This is called Lagrangian interpolation functions, or sometimes if you know the variational calculus, you might be knowing about this Kronecker delta ij. Property is delta ij is equal to 1 when I is equal to j, and it is equal to 0 when it is not equal to j, so I mean to say that this is called Kronecker delta. A Kronecker delta is a linear a Kronecker delta property is a property of a shape function E1. Similarly, when you add these values for all the nodes, in between nodes, its value will be always 1. So psi I for a particular x for a particular node value in an element must be equal to 1. This is called a partition of unity property. So these two properties must be used, will be used when you are going for P refinement to derive the values of a shape function for a different nodes of a particular element. So this is why these shape functions are very interesting. It is having interesting properties, and it is the heart of the finite element formulation. It is for this current situation, the functions are derived based on the linear assumption of u, hence it is called Lagrangian interpolation, because only u is used. If its derivative is used for deriving the shape functions, then it is called Hermitian interpolation functions, which will be there when the order of the differential equation is higher, like fourth order differential equation, as in the case of Euler-Pauli beam and many other cases. And it is having two properties. One is called Kronecker delta property, and the other is called partition of unity property. Next is when you are plotting this size in the node, its variation is linear, and it is like this. See, as I said, psi 1 is equal to 1 at node number 1. Let me rewrite this laser point. Psi 1 is equal to 1 at node number 1. Its value is 0 at node number 2. Psi 2 is equal to 1 at node number 2. Its value is 0 at node number 1. If you keep adding these values, answer is always 1. And this variation is linear. One is having positive slope, other is having negative slope. Doesn't matter. It is called linear interpolation function. And suppose if you are using this interpolation function, your answer is ux is equal to u1 psi 1 plus u2 psi 2. This is the approximate answer. See, and if your answer, your true solution is like this line, then what we are doing in this case, we are finding the solution using the linear approximation function like u1 psi 1 plus u2 psi 2 in this form. This is my final answer using one-dimensional finite element formulation, but exact answer is like this. Hence, you can say that, let me go through this pen again. You can say that this region is having error. Answers are not matched. Approximate solutions are far away from the true solution. So this particular error should be minimized. How we can minimize that? Either we can reduce the length of this element. If we reduce it, what we are getting? See here. What we are getting? We are getting the answer like this. 1, 2, 3, 4, 5, likewise. This is one approach, that is called H refinement. In the second case, what we can do? We can directly add one more node. In the interior part, and we can say that instead of linear, we are having the quadratic polynomial, so that this answer is not linear and it is quadratic in this form. So you can have the reduced error. So that is called P refinement. P refinement means you are increasing the order of polynomial. C1 plus C2x is the minimum requirement. Even you can go for the higher order. If I add one more term, then the node number is increased for a particular element. It means we are using the higher order polynomial for capturing the correct answer. That is the method of finite element analysis convergence study. Look at here. The same expressions can be rewritten in the form of local coordinate, where the coordinate system is located at x bar. So in that case, psi1 is a simple form 1 minus x bar by he, and the psi2 will be equal to x bar by he. Again, see, verify it. When x bar is equal to 0, that is node number 1. When x bar is equal to 0, which is equal to node number 1, this answer is 1. We are getting this. When x bar is equal to he, that is node number 2, this will be equal to 1. 1 minus 1 is 0, so variation is same. Similarly, for psi2, when x bar is equal to 0, node number 1, its value is equal to 0. When x bar is equal to he, that is node number 2, its value is 1. We are getting the same form. So these two expressions are the shape functions in local coordinate system, and the previous expressions are shape function for the global coordinate system. Now, using that elemental equations and elemental approximate solutions, we can derive the finite element model. The polynomial approximations of the solution within a typical finite element is assumed in this form, which we have assumed, and we have derived even the values of psi j as a function of x. So the psi j's are the Lagrangian interpolation functions of degree n minus 1. If n is equal to 2, it means 2 terms are there, 2 nodes are there, then its degree is linear because 2 minus 1 is 1. Now, the integration by parts in step number 2 of the weak form development for an element with interior nodes is carried out by interval. I am now applying the integration by parts formula for different intervals. Look at here, first element, second, third, 4, 5, 6, 7, 8, likewise x1 to x2, x2 to x3, x3 to x4, like I have to integrate it. So this is the integration. Xi to xi plus 1, same differential equation using integration by parts formula, that should be equal to 0, and it is a summation sign because we are assembling the equation. Now see, for the first x1 to xne, a du dx, this term is as it is, this term is as it is, this term is as it is. I am applying the boundary condition, upper limit and lower limit, upper limit and lower limit. For node number 1, wx1 minus a du dx, and for node number 2 minus wx2 a. This is the first element. For the second element, you are having the x2 term again, because second element is having the same first node, and x3 term. For the fourth element, x3 x4. For the fifth element, x4 xy. Likewise, you can keep adding this boundary term and put it equal to 0. From this, I can even calculate the value of x2, take the common value and write this, add these two terms here. I have these two terms. Look at here, look at here, look at here. Minus means one side is on the left hand side, one is on the right hand side, likewise. So now this term is called as a q. In the natural boundary condition, in the model boundary differential equation, we have defined this term as a secondary variable, that is q1, this is q2. I am calling this entire term is q2. This is entire term is q3, entire term is q4, likewise. So for integration of x1 to xn, a dw dx, du dx plus c uw minus wf dx, these terms I keep adding, that is equal to 0, where xie minus and xie plus denote the left and right sides of node I. So the notation which I have used for this bracket is rewritten again, that I am using q1, q2, q3 terms for this bracket parenthesis, likewise. So qi denote the jump in the values of the secondary variable in going from left to right for the ith node. How to implement it, I will take an example and discuss in detail later on. The value is 0 if no external source is applied at the nodes. Thus, for an element with n nodes, the weak form becomes this. As simple as that. This is the weak form, where I have removed this term separately and rewrite it again. xa to xb, you can again concentrate on this integral limit. It is for the elemental length only, xa to xb, a dw dx, du dx plus cuw into dx minus xa to xb, w into q dx minus this term is equal to 0, where q1 and qn represents the unknown point sources at the end nodes, and all interior nodes are qi, where which QIs are called as specified point sources, if any, at the interior nodes. If the interior nodes are not subjected to any force condition, that value will be equal to 0. Substitute the value of u, W is psi1, W is psi2 into the weak form to obtain n algebraic equations, and keep adding the values. For the first equation, it means put W is equal to psi1 here. In this case, W is equal to psi1. You will get the first equation. If I put W is equal to psi2, you will get the second equation. Likewise, you can have the nth equation. This equation, believe me, it is a correct equation in correctly typed equation. So n equations you can derive for n number of nodes. When you write this equation in a separate form or in a metrical notation or indical notation, you can have simple mathematical expression like Kij Uj minus Fi minus Qi is equal to 0. This is called finite element equation for the given differential equation for a particular element, where Kij is written as integration of xa to xb with these terms, and xa and xb are the upper and lower limit of a particular element, where Kij is for bilinear functional form. Similarly, L as a function of psi means it is called force term Fie, which is equal to xa to xb f of psi I into dx. Similarly, interpolation property might be used to convert psi I into phi j is equal to qi, because delta into aj is equal to ai. This is the Kronecker delta property. The common index is replaced by the free index in this situation. So when you derive on pen and paper, step by step, by keeping the patience, you will end up with this kind of equations, which is called finite element equations. It is a tedious task, but once it is derived, coding is very easy. And when you write a code and solve the problem, the solution time, iteration time, convergence criteria, everything you can analyze, error estimation you can analyze, and convince yourself that this is the way the finite element works. Let us go ahead, and I'll write this equation for by applying the index from 1 to n. So k11 u1 plus k12 u2 up to k1n un is equal to f1 plus fb. This is for the first, when I substitute I and j is equal to 1. Similarly, when you substitute I is equal to 2 and j is equal to 1, you will get the second equation. So in the matrix form, you can write like this: k u is equal to fe plus qe. This equation is for one element only, where k is called as stiffness matrix, f is called as a force vector or source vector, u is called as unknown primary variable, and q is called as a secondary variable. So these notations are common notations used everywhere in the research field, even that the stiffness matrix is k, u is a force vector or source vector, f is a unknown primary variable, u is unknown primary variable, and q is a secondary variable. From this equation, we are supposed to find out the unknown values at the nodal points. Primary variables we have to determine at each and every node, and that is the outcome, final outcome. When you derive the primary variable, you can have the secondary variable, which might be the outcome. If I talk about the solid mechanics problem, u might be considered as a displacement. When I differentiate u, you will be getting a strain value at a particular node, and when you use the constitutive equation like Hooke's law in simple 1D problem, sigma is equal to E into epsilon, then you can get the value of stress at a particular node value. So u, that is why u is a primary variable, and its derivatives can be calculated if primary variables are known to you. Let us derive the elemental stiffness matrix for a simple linear element. For your understanding, let us check how it is used. Again, I am redrawing the same element, which I am calling as a simple linear element. Linear means it is having only two nodes. First number node, globally it is located at x is equal to xa, and I am calling it is equal to x1. Now for I am changing the notation for second node, x is equal to xb, I am calling it is equal to x2 e plus 1. That is, node is increased, and x bar is equal to x minus xa value. So Kij in global coordinate is defined in this form, and in local coordinate this is written, this is replaced. See, this term is replaced by 0 to he, because locally the length of the element is always constant, that is he, and this differentiation is with respect to x bar rather than x. that this is bar quantity here, this is bar quantity here. It is with respect to bar. So global coordinate system and local coordinate system can be used to derive the elemental stiffness matrix, but looking to this integral formula, I can easily say that this is easy to derive the answer rather than this, because it requires more complexity, more hectic calculation rather than this second options. So I am rewriting this again. See, x can be written as x bar plus xa. Look at here. So dx is equal to dx bar, where if you differentiate psi with respect to x, that should be exactly equal to d psi dx bar, because it is a constant linear function. So this psi I can be expressed as x bar, as I have already included this expression in the previous slides, that psi 1 is equal to 1 minus x bar by he, and psi 2 is equal to x bar by he. You can differentiate with respect to x bar, and we can compute the value of kij. Now we know that index is equal to 1 to 2, maximum node is equal to 2 for a linear element. So I is equal to 1 and 2, and j is equal to 1 and 2. So 4 values of the stiffness elements you can calculate: k11, k12, k21, and k22 for a particular element. So let us find out k11. K11 is equal to integration of 0 to h. Look at here how I am calculating. I am substituting the value here. A is as it is. I am putting d psi dx bar, d psi dx bar here, plus c psi I psi j. Accordingly, I am putting the expression for psi I and psi 2 in this form, and I am integrating with respect to dx bar. So when you open this bracket and integrate it over the whole elemental length of 0 to he, you will get k11 is equal to ae by he plus 1 by 3 ce. I am very sorry, I have not included all these intermediate steps. I am giving the final answer here. ae plus 1 by 3 ce is the first element in the stiffness matrix, because I is equal to 1 and j is equal to 1. When I substitute I is equal to 1 and j is equal to 2, I will get k12. So k12 is determined by, again, by integrating this expression and putting the limit of 0 to he, you will get minus ae by he plus 1 by 6 ce, and when you interchange the indices, you will get the same answer. So k12 will be equal to k21. If you are having 2 cross 2 matrix and if the off diagonal elements are same, it is called symmetric matrix. So k12 and k21 are same in this case. Similarly, k22 can be determined. Its answer is ae by he plus 1 by 3 ce. So these are the 4 elements of the stiffness matrix. And similarly, you can calculate the force vector by substituting the value of size and integrating over the domain length of element, that is 0 to he. You will get 1/2 FEHE. Similarly, second expression 1/2 FEHE. You can see half of this value is transferred to node 1 and half of this value is transferred to node 2 in the case of force vector. So when I add all this, you will get the simple expression: stiffness matrix K is ae by he. Stiffness matrix is ae by he, 1 minus 1 minus 1 1 plus cehe by 2 2 1 1 2, and the force vector is FEHE by 2 1 1. This is called linear element. Similarly, for quadratic element, you have to add one more node. In this case, you add second number node in between. Then the location of this node is user's choice, I can say. If it is exactly at the center point, this value is he by 2. It may be shifted here and there depending upon the criticality of the conditions. If the mesh size is defined near the crack point and any critical junction, then this node must be shifted here towards node number 3, so that you can capture the field variable effectively. So the interpolation properties can be used to construct the Lagrangian interpolation functions of any degree. Any degree means it may be of 4th degree even, maybe 5th degree even. So please be careful about the node numbers. I am putting one number, second number at the center point, and the third number is at the last. And using this expression, I can write the values of psi 1, psi 2, and psi 3 like this: 1 minus x bar by h, 1 minus 2x bar by h. I can directly calculate using the interpolation property of size by substituting the proper value of x bar in for node number 1, node number 2 likewise, because psi vanishes for other nodes rather than the same node. So that property is used, and here it is an example, so I'm not going into the detail of that. Believe that these are the three values of the shape functions for the quadratic equation psi1, psi2 and psi3 in local coordinate system. So when you represent this variation, it looks like this. Psi1 is equal to 0, and it varies. So psi2 will be equal to 0 at node number 1, at node number 3, and it is equal to 1 at node number 2. Psi1 will be equal to 1 at node number 1, and other nodes it is 0, and it varies quadratically. So this is the variation of the interpolation function. When you use this quadratic equation and get the value of k11, k12 and k22, then you will get this expression by integrating this polynomials, and after substituting the upper and lower limit, you will get the answer of k11 for a particular element of a stiffness matrix. K12 is this, and we know that it is a symmetric matrix now, so I am getting the same answer of k21 even by interchanging the I and j's, and similarly k22 can be determined using the same expression of f. After substituting the values of psi1, psi2, psi3, you will get this answer of f1, f2 and f3. I am simply reading these lines, these equations right now, and believe me, you have to use your pen and paper. Same thing is repeated again and again. This needs patience to derive all these expressions. Then and then you will get a feel how to use this and get the final answers. Once I substitute these values, I'll be getting 3 cross 3 matrix of stiffness, because now you can see what will be the size of the stiffness matrix. The size of the stiffness matrix depends upon the degree of freedom used for finding the unknown variables. If the maximum number of nodes are 2, the size of the matrix will be equal to 2 cross 2 in one-dimensional problem. If the maximum number of nodes are 3, it means for one-dimensional problem, the size of the stiffness matrix will be equal to 3 cross 3. Out of this matrix, out of this 3 cross 3 matrix, you can have the main diagonal elements and the off diagonal elements. Off diagonal elements are always same, hence the stiffness matrix is always symmetric. Main diagonal elements are always positive in this case C. So using this quadratic equation or linear equation, you can determine the unknown primary variables. Once you derive the stiffness matrix for a particular element, you are supposed to again connect all the elements and find out the global stiffness matrix for the entire domain. So you must know the methodology of connecting the element. Let us see. The assembly of elements is carried out by imposing the following 2 conditions. The first condition: if the node I of the element omega E is connected to the node J, like this, see, if I node is connected with the J node and J node is connected with the K node, like here, this is the first element, this is I node of the element first, that is E element, this is the J node for element F, and this is the K node for element C. And if these 3 elements are connected together, then the primary variable should be continuous. It means this value of U should be unique, same. UIE is equal to UJF is equal to UKG. If this condition violates, then it is very difficult. It is not possible. So if node I is of the element E is connected to the node J of element F and node K of element G, the continuity of the primary variable U requires that UI for the Eth element is equal to UJ for the F element and UK for the G element. This is the first requirement. Second requirement is for the same 3 elements, the balance of the secondary variable at the connecting node requires QI plus QJ plus QK is equal to capital QI. If capital QI is equal to 0, this should be 0. If capital QI is some value, then the summation should be that some value. So where I is the global node number assigned to the nodal point that is common to the 3 elements, and QI is the value of externally applied source. And when you connect this together, this is the first element. See, this is the first element with n number of nodes. This is the last node of the first element, first node of the second element. These two nodes are connected. So these values, the addition of this value should be equal to the externally applied source. If it is not applied, then this is 0. And the primary variable at these two connected node must be same. Look at here, it must be same. And see, the order of this polynomial is nth, so I am getting this nth polynomial equations. I am not saying that it is a linear equation, so the shape function is not like this. It is nth order polynomial, hence these lines are wavy in this case. But here the value is u1, here the value is un for the ith and u for the nth node. Similarly, for the second element is having m node. Connected, value should be unique, primary variable should be continuous, secondary variable addition should be equal to the externally applied source. Now when this is connected, as I said, addition of this qn for the eth element and q1 for the e plus 1 element, it should be equal to externally applied source. Look at this example. Look at this example. For node number 2, nothing is specified. For assume that you are given a simple bar problem, and the first end, this left hand side end is fixed. At the right hand side end, at node number 3, I am applying the external force F1. And if I ask you to write the secondary balance equation for node number 2, you must know that Q2 for node number 1 and Q1 for node number 2, the addition should be equal to 0 because nothing is specified. For the second case, look at here. Force F2 is already applied at second number node. It means Q2 for node number for element number 1 and Q1 for element number 2 will be equal to F2. It should be balanced because it is externally applied. So this is the way when you assemble the elements, you have to impose these conditions. Now this is not interested at this moment. For the nth equation of element, it must be added to the first equation of the e plus 1 element. So it is the elemental addition. This addition is required to assemble the matrices. Rather than using this indical notation right now, I will use the matrix notation in the next slides and show you how the elements are added. But you must know the properties of the stiffness matrix. The stiffness matrix is always a symmetric matrix. First is Kij is equal to Kji. The entries along a main diagonals are always positive. It means Kii is always greater than 0. Sum of all elements along any row and column is 0. This is interesting and important property even. It is always positive definite for structural problems and for governing differential equations that are self-adjoint, means second order, fourth order, sixth order equations, where you can easily apply the integration by parts formula. And the global stiffness matrix is banded. What is the interpretation or what is the meaning of banded matrix? It will be clear within a minute. But let us read it again. The stiffness matrix is always a symmetric matrix. The size of the matrix is always equal to the degree of freedom cross degree of freedom. For one dimensional problem, for each node, the degree of freedom is 1. Hence, for one element, 2 nodes are there. Hence, the stiffness matrix size is 2 cross 2 for one dimensional problem. If you increase the number of nodes in the same element, then the size will be increased by 1 order. That is 3 cross 3 and 4 cross 4 likewise. The entries along the main diagonal are always positive. That is Kii is greater than 0. Sum of all elements along any column and row is 0. It is always positive definite for structural problems and for the governing differential equations that are self-adjoint, and the global stiffness matrix is banded. Now what is banded matrix? See, a square matrix whose only non-zero coefficients are located on or near the main diagonal is called banded matrix. Let us take this example. Look at here. If I add all these stiffness matrix for all the elements, you may end up with this kind of global stiffness matrix, where you can see this is the main diagonal. Just a minute. This is the main diagonal, and from the main diagonal, non-zero entries are always located near the main diagonal. Look at here. These are the 0 entries which are always located away from the main diagonal. So we can use this property while we are writing our own code, and we can save some storage of the computer so that computational process is faster. In that case, you must calculate the bandwidth of the matrix. So what is half bandwidth? That is defined as the greatest number of coefficient of stiffness in any row of the stiffness matrix from and including the leading diagonal to the outside right hand non-zero coefficient. It must be calculated as 1 plus j minus I, where I is, for a row I, find the column number j of the last non-zero entry. Then you can use this equation to calculate non or half bandwidth. Again, I'm saying this will be used only in the coding to save the space for the storage. Then the positive definite matrix means a symmetric matrix is said to be positive definite if all its eigenvalues are strictly positive, and for positive definite matrix this condition should be satisfied that x transpose into ax should be equal to 0. X transpose is a vector into multiplication of a into x. If it is greater than 0, then it is called a positive definite matrix. Look at here, I am calculating the bandwidth. This is the maximum number of column where the entry is non-zero. Afterwards the entries are 0. So, and we know that this is a symmetry matrix. There is no point of storing this data. I can find out the size of this matrix, and I can reduce the matrix size. Look at here, this is the main diagonal and this is the last diagonal beyond which all the coefficients are 0. So how to store it? You can directly write this matrix. The first column in this matrix is the main diagonal, second column is the second diagonal, and this is the last diagonal beyond which all coefficients are 0. So total number of equations can be reduced because we are using the property of the stiffness matrix. Now look at here how I am doing the assembly of the two elements. At node number 1, I am saying it is u1 of 1. u1 of 1 means for first element, node number 1 is having the field variable is u1. For the first element, that is u1, this is node number 2. At the same location, for the second node, first local node is situated, and this is the second number element, second node is situated. Globally, when these two elements are connected, this must be equal to capital U1, capital U2 and capital U3. Locally, it should have U11, U21. Locally, for the second element, it should have U12, U22. So for element number 1, if I want to write the elemental stiffness matrix, I must use K111, K121, K211, K221. This superscript indicates the element number. So this is the equation number, element number 1. This is element number 2. Even for my own reference, I am writing this 1212 reference, which is the global node numbering. So when I add this, look at here, this row and this row is K11. K11 is not located anywhere, but this row and this row is K12. Okay, so this K12 and this is K22. This K22 and K22 is available even here. So when I add it, I will get the addition of K22 and K11 for the first node and the second node. So this is the assembly of the two elements, and this matrix is called as a global stiffness matrix. And when you open this matrix, you can determine the unknown values of U1, U2 and U3. From this you can have the idea of unknown primary variable at the nodes, and by taking the derivative you can find out its secondary variable, like it may be a strain value, it may be a stress value. And we know that for a linear problem the continuity requirement is only imposed for the primary variable. Secondary variable may be discontinuous in this fashion. So this is how the entire finite element formulation is done, step-by-step procedure. I have discussed only the one-dimensional formulation. You must follow the strategies. You must know the detailed the mathematical expressions for the integration by parts. And for the one-dimensional problem, it's very easy. but for when it comes to the second dimension, means 2-dimensional and 3-dimensional problem, the mathematical aspect is very tedious. That is why the coding is generally used. And let me clear you honestly, since I have discussed the mathematical aspect of the finite element analysis, second aspect is very interesting when you are using the softwares, is the element selection. I am hoping that during this 5 days STTP, 1 or 2 sessions might be based on the selection of elements for a different application in engineering. Because if I take a simple example at this particular point, that let me take the example here. It is you at least you must know this example, that if I give you a beam problem, like a simply supported beam, and it is subjected to a force, concentrated force, and it is supported by a pin support and roller support here. In this case, you can assume that this is a 2-dimensional problem. We know that in the 2-dimensional problem, those who are having any experience in finite element method, you can select the 4-noded quadrilateral element. Nodes are 1, 2, 3, and 4. If you keep using this 4-noded quadrilateral element, and if you model this beam by dividing it into the 4-noded elements, and if you solve the problem, you will get the answer. Software will give you the answer, but the answer is always wrong. The reason is, when the beam is bended, when the beam is subjected to the point force, it should bend. When it is bended, the element should be even bended. It means it should become like this. And in the case of 4-noded quadrilateral element, the final deformed shape is like this. So this kind of problem is called as a shear locking problem. Element is locked, so it cannot capture the bending stress properly. So when you are using the softwares, element selection is interesting and important aspect for different applications, even for the thermal problem, even for the solid mechanics problem, even for the manufacturing problem. Element selection is interesting. That is why when you are learning this finite element course, your first task is to go into the detail of the basic formulation of the finite element analysis, how you can derive the elemental equations, how shape functions are used, how Gaussian points will be used in 2-dimensional case or 3-dimensional case, because it is always integration, and the unknown quantities are measured at the nodal points. So if you are taking 4-noded quadrilateral element, and if you want to find out the values of at the 4 nodes, it takes major processing time. If I select one quadrature point, Gauss quadrature point at the center, and if I extrapolate the values at the nodes, it will take it always take a lesser time. So I am hoping that when your 4 or 5 days are over, you will be having a brief knowledge about the integration, numerical integration concepts, and the coding concepts even, and sometimes you might be having some hands-on training session or ANSYS, so where the instructor will discuss the important aspects of selection of elements for different cases. I'll stop at this particular point, because finite element formulation process, which I was planning to cover, is already covered. So if you guys are having any queries in this particular formulation, please you can ask me. Hello.
One minute. 1 minute, sir.
Okay.
Just 1 minute, sir.
No issue. You can take your own time.
Okay. Participant
Please, if you have any questions, ask. I just unmute all the participants. Yes, participants, you can ask any questions if you have.
Hello, sir.
Yeah, hi.
I want to ask one question. So there are two conditions. One is that is continuity condition, and another one is compatibility condition. So what is the meaning of compatibility?
Compatibility means the differentiability conditions. Differentiability conditions means when you look at the weak form, in the weak form, if you are having the first order differential equation, then you have to guess the approximate functions which are compatible with that particular term. So accordingly, you have to select the order of the polynomial in that case.
Okay.
And continuity means at a particular node, you have to you must get the common value of a primary variable. That is why it is called a continuity.
Yes. Okay. Thank you, sir. And also, sir, there is another question. What the Gauss point is used for? Means what is the significance of Gauss point?
Gauss point is what? It is generally a numerical method. If you talk about the four-noded quadrilateral element, which I have not discussed later, unfortunately, but for the four-noded quadrilateral element, if you keep applying this weak formulation and finding the answer at the four nodal points, it will take time. Rather, if you select the center point, which is called a Gauss point, and if you integrate at that particular point, you will get the value at only one point, and then you can extrapolate the things and get the values of all 4 points. That is why you can save the computational time.
And sir, miss accuracy remains same or it differs?
Accuracy, in some case, accuracy may differ slightly. That is why you can even increase the Gaussian point. Rather than 1, you can go for 4 even. So Gaussian point can be increased. If your problem is tricky, and if your solution should be accurate, in that case you must go with the more Gaussian point rather than a nodal point, one Gauss point.
Okay. Okay. Thank you, sir.
Any other participants want to ask question? I think, sir, participants are satisfied with the lecture, and I thank you so much on behalf of FDP team and Mechanical Engineering Department, Government Engineering College Bharuch, to spare so valuable time for us, and we'll see ahead for more lectures from you. Thank you so much, sir.
Thank you very much, madam.
Yeah, thank you, sir.
Thank you, Desai sir, for joining.
Yeah, hi, sir.
Thank you very much, sir.
Bye.
Dear participants, now we will join at 3 hours 10 minutes, and you can have a break till that time.
हमने हो पावला हमने हो चा पाओ
Good afternoon, all of you. Welcome back to the third session of day 2. I again welcome Kailash Jagtap sir. He'll continue with the lecture. Kailash,
Yes, thank you, ma'am.
yeah, good afternoon, sir.
Very good afternoon, ma'am. Yeah, I hope my screen is visible.
Yes, ma'am. Yes, sir. Yes, sir.
Yeah. Okay, so yesterday we saw the complete process analysis procedure along with the modeling, meshing, and processing and post-processing part, right? So today we'll solve two more problem from the mechanical side. One will be from thermal analysis, and another will be from modal or vibration analysis. We can say, okay, I'm just going to take a simple problem so that you can understand the procedure. Since we have limited time, so I could not take detailed examples. So quickly we'll solve and then we'll move to the fluid part. So then we can discuss about the fluid CFD analysis. Okay. So let's start. So for thermal analysis, you have to take a static thermal analysis system, sorry, steady state thermal analysis system. So you have to drag this steady state thermal analysis system and you can drop it over here. So here for this you can import the model. So I already have the model with me, so I'll just import the existing model for this. So just give me a minute. Okay, so this is the pump housing that we are going to use over here, and just open the machine. Once you open imported the model, then you don't need to worry about the model. So if it is required to go for the repair work, then definitely you have to go to the specs claim and you have to repair it. Okay, but I'm using a model which is completely repaired, so I don't need to go for the repair work. Okay. Okay, so let's start with this. Here you can see the status, whether it is working or not. So here you can see it is showing starting mechanical. So still it is working. So we just need to wait until it will open it completely. Okay, so you can see this is the pump housing. So first of all, I'll explain you all the boundary conditions, what we are going to have over here for this particular problem. So this all inner faces, okay, whatever you can see inner faces over here. So those are in contact with the fluid of a pump, okay, which is at 90 degrees Celsius, okay. And this mating surfaces which are in contact with the other part of this pump housing which is at 60 degrees Celsius, and then we have the outer surface which is exposed to the atmosphere at 20 degrees Celsius. Okay, so we have to apply these boundaries for this particular problem. Okay, so as you can see, we have imported the model. You can check out this model over here. Okay, if you want, you can change the material. So we'll go with the default material, that is structural steel. If you want to change to new material, you're supposed to add that material first. Okay, from this engineering data sources over here. Okay, so then we have to create a mesh. So you can see, first of all, physical preferences is all already set for the mechanical, so no need to worry, just need to give the sizing. So let's say I'll give sizing of 4 mm. So make sure that you are working in units. If you are working in meters or centimeters, so you need to change the units over here. Okay, once the sizing is given, let's generate the mesh. If you need, then you can refine the mesh again, no, after checking if the mesh quality is good or not. Okay, but it is preferred every time to not give directly smaller size at the initial stage. So it's like a trial and error. You need to check with the different sizings. Okay, so uh, here you can display the mesh or cell elements. Okay, so still we can improve the mesh. Let's say I'll give 3 mm sizing and again generate the mesh. Okay, still it is improved. Further also you can add it if you wanted to apply certain sizing to any specific surface, that also you can apply it. Let's say I wanted to apply specific sizing on these two locations. Here you can see the sizing is small, like coarser as compared to other locations. So let's say I wanted to add here as 3 mm. So select both the faces. Okay, and then go to the mesh, right click, insert sizing. So here you can see you can apply the face sizing. Let's say I'll give sizing of 2 mm to these two faces. Again, right click on mesh and generate mesh. So like this we can refine the mesh continuously, and that will give you the best preferred mesh. Okay, so now you can check the mesh is improved in these two locations. Okay, so like this we can improve the mesh as required. Okay, and once this is done, now we can move to the next part, that is we can go for the applying boundary conditions over here. So first of all, for thermal analysis, what boundaries we have to apply? We don't need to apply these like fixed support or forces, right? So here only thermal related boundaries that can be applied. If your component which is under loading, and again it has certain temperature input over there, or temperature conditions are also available, in that case you have to combine two different analysis systems. So one is a static structural, and then second one is a steady state thermal. So like this you have to combine them together, and then you can work on it. But in this case we are just applying the normal, like a thermal related boundaries only, so no need to apply any fixed support forces, anything. We are just applying the temperature conditions over here. So right click on steady state thermal, insert temperature. Here you can check out the temperature conditions you can apply on these surfaces. So you can say, for if I wanted to apply to all these inner surfaces, I need to make sure that I have I have to make sure that all the surfaces are selected. Otherwise, what you can do is select as one surface and then go to extend to limit. So you can see automatically it will select all the inner faces until a limit. Okay, so until you have any sharp edges, it will select all the edges. So here you can see fillet is there, so all the faces are selecting. Here chamfer is there, so it is not selecting this face or the any other face. Okay, so until it has all the smooth faces, it will be selecting all those when you are extending to the limit. So click on apply, and here give the temperature. Now temperature is 20 degrees Celsius. Again, if unit is in Kelvin, you have to change the units over here to degrees Celsius. Okay, so it's 90 degrees Celsius, and then apply another condition on this face. So select this face again, right click on steady state thermal, insert temperature, and here we have temperature of 60 degree on the meeting face. Now we have to give the temperature condition to the outer surface, that is 20 degrees Celsius, which is exposed to atmosphere. So what condition will be there? There will be convection heat transfer coefficient. Okay, so we have to apply the convective heat transfer coefficient. So for that, right click on steady state thermal, go to insert convection. So in convection, you have to first select the geometry. Again, select any face and extend to limits. So all the faces will be selected. Okay, so click on apply, and here you can see now this film coefficient, this value, now I wanted to import it from the temperature dependent data. So import temperature dependent, and here we are taking this stagnant air simplified case. Okay, so say okay to this, and automatically this value will be given. If you want, you can directly put manually this value, and then ambient temperature is 20 degrees Celsius. So give the ambient temperature over here. Done. So all the boundary conditions are given and problem is ready to solve. So right click on steady state thermal and click on solve. Okay, so it's solving here, you can check it. Okay, so model is solved, and now we can go for the post processing. So here we can check out the results. So right click on solution, you can go for the thermal results, that is temperature, and you can go for the total heat flux. Okay, so we can add this result. Again, right click on solution and evaluate all the results. So once the results will be evaluated, we can get the complete temperature data. Okay, so you can see from start to end. So this is how you can do the thermal analysis. Even you can find out the heat flux results over here. Okay, you can hide this mesh results. Then you can go for the smooth contour. Okay, and then you can check out the heat flux results as well, and here you can see the vectors for the heat flux results. Okay, you will get the maximum and minimum temperature data over here. So what is the maximum temperature, minimum temperature, and the average temperature that we have? Since it is a metal, so you can see complete heat transfer is happening from one surface to another surface, right? So you can see on the outer side also same temperature which is there on the inner side. Okay, so this is how we can do the thermal analysis. I hope it is clear to you. If you have any questions, you can ask. Otherwise, we'll start with the next part, that is model analysis. Any questions? Okay, so for model analysis, we need to take another analysis system, that is model. So select this model analysis system, and here we can find out the results for various mode shapes. Okay, so at certain frequencies where we are getting the maximum excitation, so we can find out all those maximum excitation frequencies, and we can find out what is the maximum deformation at that specific frequency range. Okay, so that can be checked out, that we can check it out over here. So here, first of all, we need to create a model. So we will just simply create a simple 2D plate over here, okay, in 2 dimensions. So we will not add the thickness. So thickness, even though we are creating a model in 2D, we need to give the thickness. So that we will check how we can get the thickness. So let's say it's for 50 by 100 mm plate we have. Okay, and let's add a hole at the center, let's say. Okay. Okay, and now we need to delete this whole part. Okay, so just select it and delete it. So you can see now the plate is ready. So we can go back to the workbench and launch the model, where we can create a patch and solve the problem. Again, for model also you can have a predefined stress values or stress conditions. So that can be also taken in the same way. You have to combine the structural with the modal analysis. Okay. Okay, so you can see again we have launched the mechanical over here, and you can see this surface, and next to this surface we have this question mark. So what it means, so there is thickness that has to be given. See, in mechanical, whatever problem you are dealing, so thickness matters to get the result, right? So only when you are solving in 2D, what exactly going to happen, so you will get results only in two direction, you will not get the results along the third direction. Okay, but you have to give the thickness value of that. Even similar in case of 1D also, you have to give the cross section, but like the results you will be getting only in single direction. So let's give a thickness of 2 mm, and then just create a mesh of 2 mm sizing. Right click on mesh and say generate mesh. Okay, so mesh is created. You can check out the mesh. Still we can improve the mesh. Let's give 1 mm sizing and again solve the mesh. So here you will be able to observe one thing. Along the thickness, you will have only one element when you are dealing with the 1D problems. Okay, so that is the difference you will get over here. So you can see 1 mm thickness mesh is created, and now what we need to do is we have to give the boundary conditions, that we have to fix this model. Okay, so to fix this model, you have to go to this model, right click, insert, and here you can insert the support. So let's say we'll go with the fixed support. So go for the fixed support, and let's say we'll fix the model at four corners, so at a vertex point. So select 1, 2, 3, and 4. All vertex are being selected. Model is fixed. So this way we can completely fix the model. Okay, and once model is fixed, now we can apply the boundary conditions. Sorry, we can solve the model by giving the number of mode shapes we wanted to find it out. Okay, so here you can check out, so maximum modes to find out, here we have 6 modes. Okay, but you can give as many number of modes you wanted to find. Let's say I wanted to find out 8 results for 8 mode shapes. You wanted to find out 8 different frequencies along with the deformation at those maximum excitation frequencies. Okay, so that is what we are going to check out over here. So give the number of mode shapes, that's all. You can just right click on model and solve. Okay, so problem has been solved. You can check out, you got a green tick over here, and then you can very easily just go to the solution. When you select the solution, now this time it's not the same way, right click and insert the solution. Okay, so what you have to do is, sorry, you don't need to add it like this, I'll just do it. And you have to select the solution, and when you are selecting the solution, you are getting this graph over. So right click in the graph section, click on select all, again right click and say create mode shape results. So it will create the mode shape results for each mode shape, and here you can check it out, and you will get a complete detailed result. So just right click on this and evaluate all the results. So you can see 8 different frequencies you will get, at which you are getting the maximum excitation in a different ways. Okay, so first of all, let's see the deformation for the first, that is frequency of 561.13 hertz. You can check out the frequency. You can check out what is the maximum deformation for this particular frequency. Okay, here also you'll get this value: maximum deformation, average deformation, minimum deformation. Okay, so like this you can check it out. Similarly for second, third, so you'll see it will have movement in a different way at each mode shape. You can check it out. Okay, you can animate this as well. can go with the maximum number of frames, and you can play the animation. Okay, so you can just take keep in mind what are the frequencies for this, and accordingly you can make changes if during the problem if it is going to achieve this much frequency over there, right? So that has to be done to avoid the deformation. Any doubt in this? So I hope this is completely clear to you. And with this, we'll move to the next part, that is fluent. Okay. So for that, I'll just close all this, and I'll take a fluid flow fluent analysis system, or let's say I'll take a component system where I wanted to show you the fluent meshing, that is mosaic mesh technology. Okay, so for that purpose you need to take a component system. So let's say I take the geometry first, then you have to take the um, fluent with fluent meshing, and then you have to take the results. Okay, so like this we can take it. So just first create the model. Okay, so launching this space claim to create the model. So afterwards at 4 p.m. we will be having the session for the composite. So that is the reason I'm just taking a little faster, so that we can give sufficient time for the composites as well. Okay. So I'll just create the model, and then I'll explain you the problem statement. Okay. Okay, so we have this T section type over here. I'll just convert it into a shell body. So you can say now this is complete T section pipe which is completely hollow from inside, as you can see. Okay, so it is completely hollow from the inside. Okay, and now we have to what is our problem statement. Okay, now this is a CFD problem, so we have to extract the fluid domain first from this. So there is a problem statement like there are two inlets, so this is the inlet one, and this is inlet one, and this is inlet two, and this is the outlet. Okay, so flow will be coming from inlet one and inlet two at velocities like 1.5 and 3 meter per second respectively, and at a temperature of, let's say, 303 Kelvin and 363 Kelvin from two different ends. So what we need to find out, we need to find out the velocity and the temperature at the outlet, as well as velocity and temperature distribution throughout the flow. So that is what our problem statement over here. So for that, first thing that we need to do is we have to extract the fluid domain. Okay, so to extract the fluid domain, you need to go to this prepare tab, then go for volume extract, go for the edge selection, and then select the complete inner edge loops. Okay, say okay to this, and you can see fluid is extracted over here. Now we don't need the solid part, so right click on solid and suppress for physics. So this will not take part into your further simulation. Okay, so model is ready. Now we have to give the boundaries, that is we have to give the name selection to this faces so that we can identify them in the fluent side. Okay, so select this face and then go to the groups, and here we have create NS, that is create name selection. So click on it and name this as a inlet one, uh, inlet one. Okay, then select this and create name selection. This is inlet two, and this is the outlet. Okay, so done. So like this name selection you have to give, and remaining all the faces, these all faces, these will be acting as a wall surface. Okay, so if you want you can name it, or if you don't name it, that is also fine. Okay, so like this we need to give the name selection. Once that is done, go back to the workbench, and then you have to launch this fluent meshing. So double click on this. Okay, and here now this is the fluent launcher. You can see fluent 2021 R2. So you have to enable the double precision. You can go with the more number of processors for the parallel processing. Okay, and then you can just simply start this. Okay, okay, first it is asking to update, so that it will be transferring that mesh over here. Here you can check out the progress of update. Okay, and now we can still it's processing. Okay, then double click on mesh to launch the fluent. Okay, click on start. So you can see it automatically created a complete mesh, but I'll tell you the complete steps to create the mesh. As you can see, this is polyhex core mesh. That's what it has created directly. So what we do is, first of all, click on import geometry, and here you can see you will be getting the geometry imported over here. Okay, and just need to click on update when you import the geometry. So here you will be having the option to update it. Okay, then just update the geometry. So then we can go for the next step. So you can see it is updating the geometry over here. So every time, like, you have to first import the model like this. As you can see, model is being imported. Now what we are solving, that is watertight geometry workflow. Here you have the options to select the workflow, but we have directly shared this file from geometry to the meshing. Then software knows it is directly a watertight geometry workflow. So it has directly selected a watertight geometry workflow. Otherwise, we have to select it manually. Okay. Then if yes, any question? Okay, then if you wanted to add any local sizing, that you can add it over here. If you wanted to add, just say yes. So you can give the local sizing to the complete volume. Let's say I wanted to give sizing. It's in meter now. Okay, the units are in meter. If now, so you have to be careful while giving the dimensions. Can someone mute? Okay, so you can see the I have added the sizing, and just click on update. Okay, so this face sizing will be added. Then you can go for the next step, that is generate the surface mesh. So you can see this is the maximum surface mesh it is going to generate. You can check out the maximum sizing, and then you will be getting, this is the this is the maximum sizing, and this is the minimum sizing that we are getting at different locations. Okay, so you can see these are the spots where we are getting this minimum sizing, and this is the maximum sizing. So you can even change this maximum sizing to, let's say, 0.01. So with this we can improve the mesh quality. Okay, I think we can delete this. We don't need to give the sizing, that will take more time actually. Okay, so we can give the maximum sizing of 0.01. Okay, so then you can give the curvature angle, and you can just click you can just simply generate the surface mesh. So it will generate the surface mesh first with the tetrahedral mesh elements. Okay, as you can see over here. So you can see tetrahedral elements are being created over here for this particular model. Now describe the geometry. So here we have the different options. The geometry consists of only solid regions, the geometry consists of only fluid regions, or the geometry consists of fluid and solid regions. Okay, what it means, so you, if you don't extract the fluid domain, then also you can take your geometry. When it is having only solid, then you can extract the fluid part from it. Okay, and in case if you have you have imported the geometry like this, which has only fluid domain, then you have to select the second option, geometry consists of only fluid regions and no voids. Then change the fluid boundaries from wall to internal. So we have single fluid domain, so no need to change it. And do you want to apply the shear topology? So say no to this, and click on describe geometry. Then we can update the boundaries. So here you can see there are three boundaries which it has automatically taken. So this is inlet one. You can see it automatically highlighting this particular face over here. As you can see, this is velocity inlet. Second one is the again it is velocity inlet, and third one is the pressure outlet. You can check it out over here. Okay, so just click on update boundaries. If it is not correct, you can change it. Okay, you have option to change it. If it is a wall surface or any other boundary, you can check it out. Okay, yeah, you can edit it, you can check the and check it, you can change it also. Okay, and then you can go for the volume. So this has only one domain, that is a complete fluid domain. So this region is nothing but a fluid domain. So just click on update the region, so it will be updated. If you want to add the boundary layer formation, so you can add the boundary layer mesh as well. So here, to add it, how many number of layers you need, you can give those number of layers. You can give the growth rate, and where you wanted to add only on wall surfaces. So just click on add boundary layer, and then go to the generate volume mesh. And here we can generate a polyhedral mesh. Okay, polyhedral, hex core, tetrahedral, or polyhex core. So this time we'll generate polyhex core mesh. Just click on generate the volume mesh. Sorry, actually, I think I was on mute, but I was talking continuously. I hope you saw that mesh. So that is called as polyhexcore mesh, what we created. Okay, in the middle region, whatever mesh was there, that was the hex core mesh. Okay, and in the here you can see. I think I have to close this again. Okay, so you can see this is the polyhex core mesh that we have got over here. Okay, so this is the hex core mesh, hexaedral mesh we get. Okay, in the middle volume, and then on the surface side we have the polyhedral elements. So you can see these are the polyhedral elements, and then this mesh which is joining this hex core and polyhedral elements, that is nothing but the mosaic mesh. Okay, so whatever you can see over here, so this is how it creates a very good mesh. You can even observe the complete inflation layers over here, and in the complete volume you will be getting the hex core mesh, and on the surface side you will be getting the polyhedral elements. Okay, so like this we can create a mesh with the help of fluent meshing. I hope you understood this, and then just you need to switch to the solution mode, so it will be switched to the solution where you can apply the boundary condition. So now applying the boundary conditions is very simple. You just need to add the material. You need to add the material, then you have to assign the turbulence model. Okay, so let's see all these steps one by one. Okay, so you can see this is the Fluent window where you will be able to see the console on the bottom side where you'll get any error or anything. Again, it is similar to the Fluent meshing. This is the graphics area. This is the task page where you get details of this outline, whatever you select over here. Okay, and on the top side we have a few additional tabs where some additional options are available over here. Okay, so first one, in general, you can just click on scale where you can scale up or scale down the model over here. Okay, you can change the unit for the length, and then you can close it. Then you can perform a mesh check. When this mesh check is done, you will be able to view the report quality where you can check if there is any issue with the mesh. So if mesh quality is not good, you will get to see over here. Okay, it will show you a warning like you have that mesh quality below this, so you need to improve that mesh. Okay, then in display you can check out all the boundaries what we have given. So first one is the inlet one, so you can check this is the inlet one section. Then we have this inlet 2 section, this is the outlet section, and this is the complete inner volume. Okay, so these are the name selection. Then now this is the pressure based, we are going to use here pressure based solver since we have very less velocity. Okay, so when you have the lower subsonic or subsonic, for that time you need to use the pressure based. For high hypersonic or supersonic flows, you can use the pressure based, sorry, density based solver. Then here again we have absolute velocity formulation over here, and this is going to be a steady state problem. There is no time factor is involved in this. So then add the gravitational effect in the negative y direction. So let's say minus 9.81 along the y direction. Okay, so this is the vertical direction, and the downward direction is the y direction. Okay, you can take help of this coordinate system to understand the directions. Okay, then go to the models. Here we have the various models based on the problem. You need to define the specific model. So in this particular problem we are going to add the temperature parameter. So here you have to add the energy. You have to enable the energy equation over here. So double click on energy and then enable this tick, add this tick for the energy equation. Say okay to this, and then go for the viscous SST k omega. Here you can see you can go for this palatal mass k epsilon k omega, different turbulence models which are available. You can see these are the various range models that is Reynolds average Navier-Stokes equation that you can see over here. So in this problem we are going to take k epsilon turbulence model. Okay, so select the k epsilon turbulence model and say okay to this. So model will be added over here. Okay, so these two things are necessary to get the required, or to apply the required conditions, because based on this different inputs will be asked. Then go for the materials. In the material you can see again you have two default material for this CFD, that is air and aluminum. So air is a fluid material and aluminum is a solid material. So if you want to add any new material, click on change create. Then you can go to this Fluent database over here, and here we have list of different fluid materials. So I wanted to add water liquid, so just select the water liquid, click on copy. You can see this material will be added over, but here you cannot change their properties. As you can see, I cannot edit the properties, okay, to change it. So just copy it and close. When you copy it, it will be copied on this page, this window also. Here you have option to edit their property. Okay, just click on change, create, and close it. So like this, you can add the properties. Once you have added the material over here, so you have to add that material to this particular zone. So go to the cell zone condition, select this volume, which is name of this fluid domain, and click on edit. Okay, so here you can check out. Okay, so here add this water liquid as a material and click on apply. So material is now assigned to this complete fluid domain, and then close it. Then you can go to the boundary conditions, and here you have to define the boundaries for the different uh, surfaces. So first one is the inlet one. For inlet one, we have to define the velocity inlet type. So edit this. So type should be velocity inlet and click on edit. Here you can give the velocity as, let's say, 1.5 meter per second. Okay, and then go to this thermal tab where you can give the temperature. So from inlet one, we have temperature of 303 Kelvin. Click on apply and close it. Similarly for inlet two also, type is velocity inlet. Click on edit, and then here you can apply the velocity of, let's say, 3 meter per second and temperature of 363 Kelvin. 363 Kelvin, and click on apply. Okay, and then just simply close it and just cross check this. Okay, and then go to the interior. For this, you just need to make sure that type is interior, that's all. Then for the outlet, it should be a pressure outlet. Okay, velocity inlet and velocity outlet, these are the pad pairs, so you can take velocity inlet and pressure outlet. Okay, so take a pressure at the outlet and edit this. Here you just need to ensure that gauge pressure is 0. That's all, nothing has to be changed over here. Just click on apply and close it. Then for volume, this is nothing but a wall surface. Okay, this volume 1. Okay, so this wall surface, it should act as a wall. So here you need to make sure the type is wall for this and click on edit. And again, this will be a stationary wall with no slip condition. Okay, you can give the roughness value if you have, or you can go with the default one. Then in thermal type, if the wall is also emitting certain heat or certain temperature, that you can add it over here. Maybe heat flux, temperature, convection, radiation, or mix. Okay, or via system coupling also you can take it. Okay, so we don't have anything. Just close this, and then once the boundary conditions are defined, then you can go to the next step, that is the methods. So in the methods, you can see it is a coupled scheme. So you can change the type from coupled to simple, simplex based on the problem. So generally coupled scheme gives you the faster result. So let's go with the coupled scheme. Okay, and then you can go to the report definition where you can track certain data at specific location. So let's say I wanted to track the velocity at the outlet. So surface report, area weighted average, select the outlet over here, select the temperature from this field variable and static temperature. So report file, report plot, and print to console, and here you can check the temperature monitor. Okay, and just click OK, so it will be added over. Close this. Then in the monitors, you can give the solution accuracy. Since it is a iterative method, so you have to give the tolerance, right? So you can give the value of solution accuracy of 10 raised to minus power 3, which is default one. You can edit it, you can increase it as per your requirement. So we'll go with the default value, say OK to this, and then simply go to this initialization where you can do the hybrid or standard initialization. In case of standard initialization, you can compute from any specific location. But with respect to this, all the initial case values will be taken with respect to that specific surface. Okay. So when you have more than one inlet, then it is preferred to go with the hybrid initialization where software will calculate all the initial guesses directly. Okay. So it will calculate and then it will take the initial guesses. Once it is selected, click on initialization. It will solve for 10 sample iterations, as you can see over here. And once it is done, then you can go to the calculation. So run calculation. Here give the number of iterations and click on calculate. So it will solve the problem. You will get different plots. Let's say one plot is for the contours. Sorry, not contours. One plot will be for the residual values. Okay, so you can see this called residuals, scale residuals. So you can get a residual value, and another one is the temperature which we are monitoring at the outlet. Okay, so select the temperature monitor. Okay, so you can check out both the values. When the residual plot, when it will reach to 10 raised to minus power 3, that means all the plots will go below this 10 raised to minus power 3 will get the convergence. Along with that, we can check out the temperature at the outlet. So the temperature at the outlet, it is increasing. So this is the average temperature. Okay, so like this you can solve the problem. It's solving. So when it will complete the it will reach to that specific accuracy we have defined, so we'll get the convergence. Okay. Okay, so you can say it's going down slowly, and as it will reach no, below the accuracy, you will get the convergence. So okay, so as you can see, now it is reaching below this 10 raised to minus power 3. So I will be getting the convergence. Any question by the time? Because after this, immediately we are going to start another session. So in the meantime, if you have any questions, we can discuss. Ma'am, if they are muted, okay, all are. Ma'am, can you please unmute them so that if they have any questions, we can discuss.
Sir, I'll just unmute.
Yeah. Yes, any questions? By the time it is taking, convergence, we can discuss.
Hello, is it audible?
Yes, sir. Yeah.
Yeah. There are the four methods to solve the problem here. I think
Hmm.
in the methods you said that simple, simplic. Third one is a coupled, and
Mm-hmm.
fourth is a piezo.
Piezo.
Yeah.
Yes.
So out of these four, which one is most suitable for the phase change materials?
Sorry, sir.
I'm going to analyze the phase change materials in the ANSYS, and
Okay.
out of these four methods, which method is most suitable for the analysis of the phase change materials?
Phase change.
Phase change,
Okay.
PCM.
Okay. So for that, you can go with the simple or coupled scheme. Mostly that will be more suitable. Okay. If you wanted to get faster results, then you can go with again. If it is a transient, then automatically it will be taken piezo.
Yeah,
If it
because
is,
it is
yeah, in
transient
transient.
problem.
Yes. So it will take a piezo method, and that will be suitable for the transient problems.
Okay, so piezo method gives the more accurate results than other.
Actually, piezo will be available for transit where you can go for explicit or implicit solutions.
Okay.
Yeah. Any other question?
Yeah, one more question is that you are showing here the duct in which fluid is flowing with a certain velocity,
Mm-hmm.
right? And we fix the velocity at constant. Can we
Mm-hmm.
set it at the variable speed or the variable velocity with respect to time?
Yes, you can set it. For that, you need to go for a transient simulation. You can give the initial velocity. Maybe if it is like a gravitational effect is there, then the velocity will be changing with respect to time due to the gravitational force. Or if you wanted to add, you can add some expressions. Here you can see for the variables like how the velocity is changing. So you can add the expression over here, and accordingly you can just call that in the this boundary conditions. Let's say here you just wanted to add it, so instead of this absolute value, you can go with the this magnitude value. You can add that expression as an input. So based on the variable, this expression will be changing its values, and you will get a variable velocity. So you can add it. Okay. Or if not like this, if then you can add a user defined function. So here you can see user defines, where you just need to write a simple C program for the variable velocity, and that you can compile it over here. So these are the different ways you can do it. But now no necessity to go for the functions. You can directly add that as an expression from this named expressions, and then you can call it, or you can directly define even expression here itself. Okay. From named expression also you can take it, or you can define it directly instead of this value. So
Suppose,
accordingly it will.
yes, this is the velocity 1.5, it is fixed, right? Suppose
Mhm.
suppose we are taking the case that for first 2 minutes the velocity is 1.5, and then it is increased up to the
Mhm.
3 meter per second. So can we do that
Mhm.
simple program over here
Yes,
without?
yes. You can just write a simple program in this, UDF, and you can just compile it. So automatically it will take the consideration of that particular values.
Okay, and is there any
That is
tutorials
also.
available for that?
Yeah, for UDF you will be getting tutorial how to write it, but for UDF it's like completely your way to write the program. So that is the thing, because in different person can use different commands to write that program, right? So it's completely up to the person how you want to write. But yeah, syntax and all those things are available that you can check it, like for the common commands. Okay.
And one more question is that this is the diameter of the duct. It is fixed
Mm.
right now. Okay. So
Yes.
can we check it at variable diameter, the effect of that?
That is like a parametric study, sir.
Yes,
Okay,
parametric
so
study.
if you wanted to do that, yes, you can do it. What you have to do is in a space claim, you have to set this diameter as a parameter set, and
Okay.
you can like easily create it.
Okay, but is it
Uh,
affect on the massing? Because when diameter changes, that it will affect on.
You can even set, change the meshing also accordingly. So you can set a meshing as a parametric study also. So all can be added into the parameters. So you can accordingly check it out. So what you can do is you can fix the sizing or something. Then like accordingly you can make the changes. Okay, you can fix certain proportion. So let's say you are changing the diameter by 2 mm, and you can keep the sizing constant. Let's say you are giving sizing of 1 mm itself, so definitely that will give you the more finer mesh only. So you can keep meshing constant, or if you want to decrease it, you can even go for it. But like it will be time taking if you are changing the mesh also for the different sizings. Okay, so up to you. You can make, you have control to change everything for in a parametric study. Even you can set this velocity also as a parametric study, but there you can add a fixed variables over there. So let's say this velocity initially it is 1.3. I wanted to add that as a parameter, so you can create this as a parameter input. When you create it, it will be directly visible over here. You'll get to see the parameter sets. Let's say I will add a parameter set like this. Okay, I think for this you have to give this actually while giving the dimension, now I cannot change it because it's extracted part.
Yes,
So
yes, because
yes, here you can change it because that will be changing with respect to this.
it should given in the pipe diameter, I think.
Yes, yes. In the diameter, there you will have option to add as a P. So let's say I'm changing this sizing. So you can see here when you are adding it, you will be get an option to add that specific sizing.
Okay.
So accordingly you can change it. So parameters, you can set it. You can set parameters. Let's say you wanted to change this height as well. So you can select accordingly that and this surface.
I think first of all you have to fix the diameter and then get
Yes,
the
yes,
measurement of thickness, and then we can change it.
yes. You can it's very easy and simplest way you can do this. Actually, see, while giving this length and all, that time you have to do it. Now we already done this, so like I am unable to do it. But at that particular point of time, it is very easily possible. You just need to add the parameters set over. If I will make changes now, actually the problem will be updated, and I could not. So I will not be able to solve
It's okay,
otherwise.
sir. It's okay, sir. Thank you. Thank
But
you.
it is very easily possible. You can do it. Even for mechanical, for any kind of thing, you can go for the parametric study, and you can do DOE, design of experiment. So you can do that study very easily. You can have different contours. So this you can see design exploration. So these all are these options are available for that parametric study only. So you can have parameter correlation. You can get a surface response graph. Everything you can get it over there. Then our last step, once the solution is completed, you can see here you'll get a convergence over here. And once you got a convergence, so you can say your solution accuracy is reached below 10 raised to minus power 3. And then you can go for the post processing where you can analyze the result. So here you can see I have launched this CFD post over here. Okay, and you just need to create a plane to view the different results on the plane. So let's create a plane over here. Select the plane 1 at xy and z is equal to 0. So you will be able to see this plane over here. Okay, and on this plane we can view the different results like vectors. We can check uh, on plane 1 like this, as you can see. Then we can check out the contours. You can hide this vectors. Then you can go with the contours. Again on plane 1, you can check out the pressure contour, how pressure is varying. Then you can check out the temperature, how temperature is varying inside this complete, right? So this is 363. So you can see this is how the temperature is varying. Okay, and then you can check velocity as well. So this is how velocity is changing. You can check out even boundary layer formation near the wall surface. As you can see on the wall, you will be having the zero velocity, right, due to the boundary layer effect, and then it will be increasing towards the center of the flow. Okay, then you can create animation for this. So we can create a streamlines. Go to the streamlines. You can create a streamlines on a plane or volume as well. So let's create it on a volume. As you can see, okay, and then you can animate this with the help of this animation option. You can reduce the speed, select the streamlines, and you can play the animation. So this is how the flow is taking place inside this T section pipe, and that can be easily viewed over here. You can even change this side like symbols of the ball. You can change it with anything else, like let's say you can take anything. Let's say take a fish. You can animate. You can save this in a movie format or in a video. This video you can save it. You just need to enable this save option, save movie, and here you can select the location where you want to save this, and you can save it in a in different media formats. Okay, so this is how we can solve it. To get the results at any specific location, let's say we wanted to get the results at the outlet, so we can create a line at the outlet. So let's say line 1, so it will be at the outlet, so it's to 150 0, sorry, it will be 30, sorry, 15. This will be minus 15 and 150. Oh, okay, it's supposed to be at a height, right? 50, right? 5 plus 15, 90, and 6. You can see at the outlet we got this line, and on this line we can plot, create the different plots. So go to the charts, and you can give the name of the chart over here. You can give the data series on line 1, and along x, let's say you have the velocity, and along y we have the y distance, that is the vertical distance. So click on apply. So like this you are getting the velocity profile. So like this you can get different data. You can export this data in Excel sheet file format. Okay, so like this you can do the post processing. Here also you can create a report of it, and you can save this report over here. Okay, I hope everything is clear about the CFD simulation. Sorry for moving a little faster. So since we have another session, so I will just going in a hurry. Okay, any other questions? In 2 minutes we can discuss. Otherwise, we can move to the additive manufacturing part. Sorry, the composites part. Any question? Ma'am, can you make Tushar Sharma as a presenter?
Yes, just
Yeah.
just give me 2 minutes.
Yes, so I have Dr. Tushar Sharma along with me. So he will be taking us through the composites part. Okay. Yeah. No questions in the fluid, mechanical, any of the side. Okay, then I think we can start with the composites part.
Hello.
Yes, sir.
Sir, when we open this courses.ansys.com, no, we're getting
Mhm.
free student software. Can we download this as a faculty?
Yes, you can download it, but it has it has many limitations. You can download it, you can work on it. It is
Kailash,
valid for 1 year. Yes.
Kailash, sir, as a faculty, you can download it and you can use it, but you cannot do work as per the company policies, sir, because that software is meant for the students
Okay.
for learning part to know how the ANSYS works. So if we go into the technicality of the name itself, it is a student version part.
Yes,
So
yes,
we
yes.
yes, sir. So we will not recommend you to work on it. Yes, but you can download it and you can check it whether what all features are there and what Kailash have told you regarding today. If you wanted to practice it also, for that sake, it is fine. But if you are thinking to
Okay, fine,
do
fine. That
any,
is what actually I want to have. Yeah.
yeah,
I
yeah, yeah,
can,
yeah.
no, no, I'm not
But it,
able to do the projects as of now, but
yes,
I would
yes,
like
yes.
to practice what sir has explained from yesterday onwards.
Definitely, for that purpose, for 2 days, 3 days, faculty can utilize it, but it is generally meant for students part.
Okay, and we can we have the tutorials also, sir, for this?
That Kailash,
I will share this file, sir. So by checking this recording, you can work on it, right? I'll share the required files for this. Okay.
Okay, sir. Thank you, sir. Thank you.
Yeah. Yeah. Thank you. Yes. And I think we can start with the session, sir.
so shall we start?
Yeah.
Okay. So very good evening to all. So myself, Dr. Tushar Sharma from ARK. I am a technical manager and looking aside for a structural related domain of ANSYS. So I hope a fluid related material Kailash have given you a decent idea about the CFD side. So as requested, I will be taking you to the tour of ANSYS composite domain part. So since we have already left with a very less time for today's session, so quickly what I'm doing is I am directly taking you towards the tool. Okay, and I'm skipping the presentation part. What all are the advantages of composites? What are the composites and what all things we can do through composites part? Then what are the ANSYS features of composite? Instead of that, directly I'm taking you towards the tool. Okay, because we have very less time today. So please confirm if you can able to see my screen.
Yes, sir. It is visible.
Okay, so this is our workbench window. Okay, where already you might have seen all the analysis system like ANSYS CFD, CFX, Fluent, everything will be there related to the CFD part and related to the structural, static structural is there, topological optimization, transient structural, transient thermal, all the analysis system is there. Along with it, the component systems are also available. So for starting with a composite problem, first let me showcase a complete problem to you. Okay, so what problem I am taking? So into the demo part, this is my problem which I am proposing. Okay, this is a very basic problem. I usually do it with the students part. So I thought of doing again with you. It will give you the fair enough ideas and the steps which has been required to set up a complete composite problem. Based upon this step, you can proceed it further with your specific geometry. So for the sake of completing the composite problem, I have taken a composite sandwich panel. Okay, so this is the composite plate, composite sandwich panel plate. You can say the dimension is 300 mm cross 300 mm cross 16.6 mm. So length is 300 mm, width is 300 mm, and the thickness is 16.6 mm. So inside the if you go into the thickness wise direction, into the thickness you can see there will be a 1 mm 1 mm thickness at a bottom face. Okay, 0.6 mm thickness at a top face, and in between a 15 mm core is there. So since we are utilizing core in between, it become a sandwich. The bottom surface and the top face both will be of fibrous composite, and in between we have taken some foam. Okay, so the maximum thickness will be covered by the foam, or we can say a core. Above one will be a 0.6 and the below one will be the 0.5. And above face sheet, top face sheet will be having a 3 layers. Each layer is having a 90-degree of orientation of fibers, and below will be having a 5 layers, and the stacking sequence for the below bottom face sheet will be minus 45 degree, 45, 90 degree, minus 45 and 45. So this is the information which is being required before solving any problem. So we can say it as a prerequisite requirement for any solving any problem. You should know the dimension of it. You should know what we are doing with the geometry and the inside story of it. What should be the orientation of fibers? What are the thickness of it? Okay, and once we are done with the modeling part, then we require the loading and the boundary conditions. So boundary condition will be the all side will be fixed of this particular sandwich panel, and the pressure of 0.1 megapascal will be imposed onto it, onto the top face. Okay, so basically this is the complete information which is been required to set up a problem. So based on this this problem, we will be setting up our composite problem in ANSYS ACP. So now to start with, I take it from a component system part. So I take it ACP pre. Okay, you can ACP pre is a preprocessor, ACP preprocessor, and ACP post is ACP post processor. So for setting up a problem, we will be starting with ACP pre. Okay, so in this, first of all, I need to add the geometry. So instead of going into opening the space claim geometry and everything, what I'm doing is I'm recalling the geometry directly from our database. That is a very simple plate. If you wanted to look at, I will show you. It is a very 2D plate, simple. And says space claim is opening, and now you can see this is my simple plate, what we are using it here. Okay, now go back to the engineering data, double click onto it. Into the engineering data, you can see the structural steel by default material is present there. Okay, so now I need to add my composite material property. For adding those composite material property, you need to go into the engineering data sources, click onto it. Okay, Now in a data sources, you can see there are different data source available like Grenta source, journal material, additive manufacturing, geomechanical composites. Since we are dealing with the composites, so just click onto the composite material. Once you click it, the outline of composite material, what all materials are available in the composite material data source will be visible. So the first thing is that uh, you should choose precisely your material property. So here I am using epoxy carbon woven pre-packed material property for my composite, that is for the top layer and the bottom layer. Okay, and for in between there is a foam, so I am utilizing a SAM foam. Okay, so I have taken a SAM foam 81 kg per meter cube one. So these two material property I have added. So now these two material properties are also been added up in our project part. So you might be thinking that why I have taken the mixture of epoxy and carbon woven. Okay, so let me clear this through one slide, which will clear your doubt. Yeah. Okay. Wait. Yes. Now you can see it here. In composites, basically there are three approaches. One is micro scale approach, then there is meso scale approach, and another is macro scale approach. Okay, in a micro scale approach, what we are doing is we are taking the material property of individual component. For example, we are considering fiber separately and we are considering a matrix separately. Uh, and for both of them, we need to provide the material property. Then what will be the volume fraction? What is the fiber dimension? Every information is being required for mesoscale. Then it will predict the complete mechanical property of it. Okay, then it comes a mesoscale approach. A mesoscale approach, we also called it as a ply level approach. So particularly ply a material information is being required for dealing with the mesoscale approach part. Okay, so for a particular ply, what is the material property and what is the fiber orientation is being required. And for macro scale approach, a laminate level, a complete material property of entire structure is being required. What we usually do in our static structural part, we are imposing a complete material property into it. Okay, so that is, we call it as a macro scale approach. So you need to remember ANSYS composite pre-post always work on the mesoscale approach. Okay, so mesoscale approach is a ply level approach. In one particular ply, there will be a combination of fibers and a matrix. Okay, so due to that fiber and matrix, what is the material property? And if the fiber is been oriented along particular direction, so based on that direction, what is the change in the mechanical property is we are calculating and imposing into our mesoscale approach part. So why I'm telling you that is, since now you can see for a single particular ply, I have taken a material property of epoxy carbon woven. So it is a mixture of fiber plus matrix. So mixture property we are at a ply level we are imposing in our material property of ANSYS ACP. So once it has been done, now open the model where we require to do the meshing. Okay, and once the meshing has been done, we need to jump into the setup of ANSYS ACP pre. It's taking time, I think so. Then now it is coming. So now you can see this is my plate, and in a geometry it is showing question mark because we have modeled it as a 2D one and it is asking a thickness. So the thickness is 16.6 mm. Okay, once the thickness has been done, just generate mesh. Meshing is also done. I am not taking a much fine mesh, otherwise again it will take a time to solve the problem. Okay, so just update the mesh and quickly enter into the ANSYS ACP part. Now, while entering into the ANSYS ACP prep, you need to remember three things basically. The first thing is that you need to define first the layers, which particular layer model you are working. Okay, then you need to define the reference direction. Based upon the reference direction, your fibers will be aligned. Then you need to define the surface onto which your plies need to be uphold, because composite will be the combination of the different angles ply. So one over another ply will be mounted over it, which we usually called as a stacking of the plies. Okay, so you need to know what is the base and what is the direction of that particular stacking. So that is also being required to define. So everything we will be defining, and based upon that we will be seeing how our composite will be modeled. So the first step is check what is the material are being aligned. As we can see, the three materials are there. Structural steel, which is by default available, and these two material, the one is epoxy carbon woven, which we kept it for the composite top and bottom part, and SEM foam we have chosen it for the core part. Okay, so now the first step is you need to create a fabric. So click on to the create fabric. So the name is fabric 1. You can name it as composite also. What is the material for fabric 1? For composite we are choosing epoxy carbon. And what is the thickness of one layer? Thickness of one layer is 0.2. Now you can check, first you can check the units here. In a MK system, the unit is in meter. If I put 0.2, it will goes into the meter. First go and change it to MPa. Now it is mm. So again, if I goes into the fabric, since it was not defined, composite material I have chosen for composite epoxy carbon woven. Thickness is 0.2 mm. Okay, and okay. So my composite one layer. So I have defined the one layer. One layer is of 0.2 mm. If you remember our slide, you can see each layer is of composite is of 0.2 mm. Okay, so one layer I have decided created of that particular epoxy carbon woven of 0.2 mm. Okay, so now another layer I am creating. This is fabric 2 and this is for core. So for core we have chosen the material as SEM foam and its thickness is 15 mm. Like okay. So now a composite layer has been created and a core layer has been also created. Now goes to stack up. Okay, create in a first stack up. It will ask you which fabric you wanted to design. So let's suppose if I am designing it for bottom. Okay, so for bottom it will be a composite layer. The angle is minus 45. Then again bottom, the angle is 45. Again bottom angle is 90. Again first one minus 45, and again first one 45. So as per my tracking sequence, you can see from bottom, if I start minus 45, 45, 90, minus 45, 45. Same thing I have given it. If you apply it and you wanted to see, go into the settings of analysis, apply angle E1, E2 and G12 and apply. Now you can see this is the Z coordinates. So stack up from bottom, you can see minus 45, 45, 90, minus 45 and 45. So this is my stacking sequence being created into the stack up bottom. Okay, so this is the one way. Now for top also, you can create it here itself. Like if I create another one for top layer, composite 90, composite 90, composite 90. So now you can see it here. 3 layers, 90, 90, 90 is also been created for the top one. Okay. Now this is the simple thing of defining it. But now the major question arises is at what particular location these stack up will be placed. Okay. So for that, first you need to define the reference direction. So what will be the reference? Okay. So for whenever you need to define any reference direction, you need to go into the row sets. So into the row sets, create a new row sets. Okay. Into the row set 1, it will be, if I take this particular direction. Okay. So now you can see there is direction 1 and direction 2. So the direction 1 is x-axis, y-axis and z-axis. So what I have taken? I have taken 1 in the x direction. It seems that 1 is my primary direction and 2 is my transverse direction. Okay. So if you wanted to change it, you can change it, but this is the x will be my primary direction. So based upon your direction, your surface, you can change your direction from here itself, direction 1 and 2. Apply and OK. So this is my reference direction. Now, once your reference direction is being done, you need to give the direction. What is the direction on which each ply will be setting up? So it will be basically Z direction, because onto this base stack up will be placed in particular Z direction. Okay. So for placing up the normal direction, what you need to do is you need to go into the oriented selection set. So click onto it. Okay. So first of all, it will ask you the element set. Which particular element set you wanted to place the stack ups. So either you can write it all, or you can select it from here itself, element sets. So all elements. Once you selected all elements, means for all the elements, this particular direction will be applicable. Okay. Now, which particular point you need to select? You can select any point. Now you can see I am selecting this particular surface. Once I am selecting that particular surface, always the normal direction will be your stack up direction. So see, this is my normal direction to that particular surface, and this which is actually your Z direction. Okay. And for giving the reference, so based on which reference direction all stack up will be placed, will be defined by our row set. Which row set? We have already defined row set 1. Apply and OK. So now you can see this is my normal direction, normal to the surface. This is the orientation of the stack up. Stack up will be placed in this particular direction, and this is my yellow is my reference direction. Reference I have placed in a x direction, so it is aligned. Yellow direction is aligned to my xy. So now everything has been defined. Just I need to place my plies over it. So for placing it, I can go into the modeling group. In a modeling group, create group model. Okay, create ply. This first for creating the first ply, what I am taking is which OSS oriented selection set we have created. Orientation selection set 1. What is the material property you wanted to place it? See, start with the bottom one. So first bottom we have created. Rest all information regarding the angle, ply, layers, everything is been given already in a stack up bottom. You need not to do anything now. Just apply. Okay. So your bottom part has been done. If I rename it, bottom. Okay, now I will create a core, which is my middle part. So for again for core, OSS will be the same. What is a ply material for core? We have selected a fabric 2 core. Nothing is been required. Again, that core is been updated. Okay, and last one is a top face. Okay, so here I am letting you know a new method also. So now in the oriented OSS, again you need to select the same which we have decided. So now either you can go with the stack up to bottom, as we have taken it for stack up bottom in the previous one, or else you can create it here itself. How to create it, I am letting you know the new method also. So take a fabric of composite. Okay, so what is the angle? Angle is 90 degree, and how many layers is been required? 3 layers is required. So this is the another way. Just apply and okay. So through that also 3 layers will be generated. Or else what you can do, you can take the stack up to top. This you need to take 0 and ply should be taken 1, because already 3 layers are been defined into the stack up earlier itself. So apply. Okay, now you can see 5 layers are being generated at a bottom, 1 layer is being generated in the core, and for top 3 layers are being generated. So to verify whether all the layers are as per the stacking sequence what we have chosen it here, like minus 45, 45, 90, minus 45, 90. Since in a foam nothing is there, we are considering it as a 0, because it is an isotropic material. And for top 90, 90, 90. Now check it. Okay, so I'm see, this is my fiber direction. If you can see my screen, this is my fiber direction. So start with the first one. The first is minus 45. This X is my reference direction. So based upon this, it is my minus 45 angle, then 45 degree angle, then 90 degree angle, again minus 45, and again 90 degree. Oh, again 45 degree. So this is the bottom one. Core is 0 degree, so align again align with the X direction, and top one is having 90 degrees, 3 layer, 90 degree, 90 degree, and 90 degree. All are 90 degrees. So this is how you can create your own stacking sequence on any of the component. Okay, so once this step has been done, okay, so Our preprocessor part is completed. Just refresh it. Okay, now what you need to do is you need to transfer this data into the structural part, where we need to impose our loading and the boundary condition. For that, what you need to do is you need to take the static structural one. Okay, the setup of this, you connect it with the model. So once you connect with the model, it will ask you whether you wanted to transfer this composite as a solid or you wanted to transfer it as a shell. Since we have modeled it as a 2D, we are taking it as a shell. Okay. Now just open the static structural one. The complete information of ANSYS ACP will be transferred to the static structural. Now we will be imposing our boundary condition and loading condition here and solving our model. But for viewing the results, since for composites, the failure is something which is we are very much interested. We cannot see it here in a static structural. We again will switch to ACP post. Okay. So now you can see into the mechanical, all the information of ACP bottom, core and top is being transferred. Okay. So quickly I will be imposing the boundary condition. So click onto the static structural, insert. I am providing the fixed support. So for fixing the support, select all the edges. Since it is 2D, after meshing it is showing as a 3D, but now you can see it as a 2D one. So I have selected all the edges and apply the boundary condition fixed support, and I will be imposing a pressure. So selecting the space, apply, and the pressure is 0.1 megapascal as per the requirement in our problem. Okay, so the pressure has been defined. Now I am taking a total deformation and I am solving this particular problem. Now you can see this is my particular problem. Okay, and for this particular problem, what is the deformation which comes? It is 2.72 mm. This is the total deformation. But if you wanted to find out the failure and all those stuff, you need to go into the composite domain again. So for reaching it out again, what you need to do is, now I am recalling ANSYS ACP post. Okay, so for ANSYS ACP post, just align this ACP post over the prep. All the three will be directly connect to the ANSYS ACP post, means material information, geometry and the model information comes into the post part, and the solution of static structural will be clubbed into the result of ACP post. So just update everything. It will take a few second time. So everything will be updated since we have connected a new connections. So let all the data to be transferred to the ANSYS ACP post. Now everything is been green tick. Quickly open ANSYS ACP post. Okay, now visit to result. So for viewing the result, what you need to do is, see the solution is already been there. Click onto the create deformation. Okay, and so now you can check for the deformation, the same deformation what we have seen into the static structural, same deformation we can see it here also in ACP post, that is 2.72 mm. Okay, but rather than this, we are very much interested in our failures. So for viewing the failures, what we need to do is we need to define the failure criteria. So for that, you need to go into the definitions Once you click the definition, it will take a failure criteria 1, which all failures you are interested in. The first is maximum stress, Taihu, then maximum strain also. Okay, and since we are modeling as a sandwich, click onto the sandwich criteria. So I am interested in core failure. So apply and okay. So once this failure criteria has been defined into the definition, again come back to the solution. In solution, goes to create failure. Okay. Now in the create failure, just simply you need to click vertical layer, and the failure criteria definition is 1. Apply. Okay. Now you can see for entire composites, okay, which is the layer failing is CF6. What is the CF means? CF means core failure is been coming onto those particular elements, and at which particular layer? Layer number 6. Okay, so how to identify core layer is, if you remember my problem statement, if you count it from a bottom, 1 2 3 4 5 6, sixth is a core. So my sixth layer is been failing, and which criteria has been failing? That is been failed using core failure. Okay, so through this information, what you need to do is you need to again redesign your structure, or you need to impose a new material property of a core through which it should pass this particular criteria. Up to this particular loading, your laminate is not been failing, your composite is not failing, but your core is failing for this particular sandwich. Okay, this information is being traced through our failure criteria. Again, I am letting you know this number is sixth layer. Okay, and your core is been failing. So this is how you can identify, and much more things are being available here to explore. Even you can do a material parameterization for with different material property, different orientation, and you can get the results of much more data at one time. Yes, it will take a long time, but that is also one of the options. Even you can trace up your stresses and all those stuff. Okay, so this is the setup of a composite problems in through ACP part. Now I will be letting you know very quickly another module of composites also, as what I was discussing yesterday. There is another tool of material designer. Okay, so in material designer, what is being there? If I have able to showcase you, yeah, if you can able to see this screen, I have discussed about a mesoscale approach or micro scale approach. Okay, in which we need to identify the material properties of fibers and matrix individually. So that is basically a micro scale approach or a fiber level approach. This approach is being utilized in material designer. Okay, so here you need to identify your material properties at a individual level. So for it, I am clicking my engineering data. Okay, so again, as you can see, for this particular structural steel is there. Again, I going to engineering data. Same thing, composite material. Into the content of composite material, you can see single fibers are there, like carbon fiber is given, e-glass fiber is there. So I am choosing carbon fiber with 395 GPa material property. Okay, and for epoxy, for matrix, I am choosing resin epoxy. Okay, so two materials I have chosen. The fabric part I have taken a carbon fiber. For matrix part I have chosen the resin epoxy from a material library. If in case you are interested to model your own material either in ACP or in material designer, you can choose your own material at any time. Okay, like I have defined a new material, new, just bring the material property and drop into the new part. It will be showcasing you here. Now you need to define the density over here. Then if you are interested in opting a orthotropic property, click here. Now you need to impose your orthotropic property. Similarly, lot many material properties are being there. What are you being interested in? Then tensile strength or any failure criteria part. So you can add up. The only thing is the material property which you are trying to add up with here. You need to add all the things. If you have not added up, it will not taking into the simulation part, and it will show you the error. Okay, so just I have removed this new part. Just I have taken it to showcase how to do it. Now my material property has been chosen. Now I am opening a material designer. I'm hardly taking 2 to 5 minutes time more. Okay, and meanwhile, if anyone have any queries, you are open to ask it so that we can wind up the session on time.
Excuse me, sir. Amarnath here.
Yes, sir.
Sir, yesterday also I had the same question.
Yeah.
So regarding metal matrix, if I want to perform about the metal matrix composite in the experimental values I am having, so how can we plot?
Sir, in experimental values, what all material properties you are finding out, you wanted to utilize those only, na?
Yes.
So
say suppose
simply,
I
sir.
want to.
Yes, sir. Please go ahead.
So if I want to perform the tensile test as you mentioned just now, like tensile test and even the yield strength or even some of the properties like hardness, malleability, we have some experimental values, and that values I want to fed on that software, like the properties if I want to fed that, will it be applicable for the metal matrix composite as well?
Yes, sir. Yes, sir. For any composites you can take it, sir. Anything.
Okay,
anything.
Sir. Okay, if I having the cylindrical value matrix like a height of 30 mm and diameter of 10 mm, and if we have the same values, will it be applicable for that also?
Sir, I think if you give me a 5 minutes time, maybe your query will be resolved.
Okay, sure.
I will come back to you again on to that part. Okay, sir. So now this material designer is been opened. Okay. So now you can see I am choosing a short fiber composite in case. Okay, and for it, first it is asking me the matrix material not assigned. So click onto the material here. It is asking what is the matrix material. For matrix material, I am taking the resin epoxy. For fiber, I am taking a carbon fiber. So I am updating my material. Okay, my material has been updating. Now for geometry, you can see the fiber volume fraction it is been asking. A seed it is been asking how much number of the seeds it is been populated into the random manner. Then orientation tensor, then aspect ratio, fiber diameter, all the information which is being predefined. I am using that part, but you can play with all those parameters. There is no issues. So in case if I think so, sir is asking about this kind of problem itself. Now you can see it here into the particular geometry. I have taken it as an align one. You can take it as, or I am taking it as a random one. You can take it as an aligned one. It is not necessary that it should be a carbon fiber itself. It can be a metal. It can be your any sort of material here, okay, which is being mixed with the another component of matrix. Okay, so I have created this RVE. Now simply I am going for a meshing. I'm not changing the size because otherwise it will take a lot of time to solve it. Sir, I think so. Similar kind of things you are asking me.
Yes, sir. Go ahead.
Yeah. So it will take a few minutes time for doing the meshing part, and then it will take approximately 5 to 10 minutes for solving it when we are doing a complete setup. So for that case, I have kept it the solution for your reference, so that I can directly showcase you the result part. But it should mesh first, then I show you the next two steps also. It's taking time. Okay, leave it. Rather than wasting much of the time. Okay, see, the meshing has been done. So once the meshing has been done, now next part is you need to go into the setting. So I am taking a simple compute linear elasticity problem. Okay, and just okay with it. Okay, and now I need to analyze it. Okay, so if I start the analyzing part, and if I goes to the another one, it will take a time. So rather than that, I have done the analysis part for a constant material evaluation with a same material, resin epoxy and a carbon fiber. Okay, so now into the results, what I am getting is I'm directly getting the mechanical property of it, like E1, E2, E3, G12, G23, G31, nu 12, nu 13, and nu 23. Okay, so this is the basic orthotropic material property which I am getting in return of setting up this complete material complete scenario. Okay, so now what is the advantage of it is that based upon your geometry, okay, you can select any of the models. Okay, so based upon your geometry, you can select any of the model, and onto that model, you can play with the material properties. Based upon those material properties, you will be ending up with the results. And the best part is, let me show. If you take on to the engineering data, okay, you can club that the output of this directly into the engineering data part. And if I double click it, now you can see along with structural steel, short fiber, resin epoxy, carbon fiber. Because we have taken a resin epoxy and carbon fiber, the complete material property of it comes here, and directly you can take this material property into your ACP part. Okay, so that is the main workflow and main advantage of it. So if I show you here, if I take it ACP prep, directly you can share that material property here. So no need to duplicacy of the work has been required. So the material property at a micro level, what you are targeting to extract it, you can extract it through here and directly route it to the ANSYS ACP at a ply level. So that is all about setting up a problem in ANSYS ACP and material designer. So now you may ask your query. I hope, sir, you got the answer to your query, but still you have any doubt, you please let me know. I will try to clarify it further.
So if you have some tutorial on basis of that, can you able to provide some?
Sir, basically on what tool, ACP or material designer?
So based on SCP.
Okay, sir, let me check if I am having any shareable documents. I will definitely share to Kailash, and in return Kailash will share to the to you all.
Okay, sir. So rest part is okay.
Okay. So anyone else is having any doubt?
Sir, good evening, sir.
Good evening, sir. Sir, I don't know whether I not able to understand your voice, or maybe it is my end.
No, from his end, I think there is a network issue, sir. Can you just check it out? Because your voice is not properly audible.
Sir, still your voice is not audible, sir. We are not able to understand.
Put in the chat box.
Sir, definitely you can put it onto the chat box, sir.
Sir, there is one question in the chat. What will be the procedure to perform vibration analysis on same composite plate?
Sir, same thing. The composites for doing the vibration analysis, if you are doing a pre-stress vibration analysis, just you need after the static structural one, you need to add up the vibration domain into it. If I showcase it here, this is the static structural part. Just after this. Visible. Okay. Wait a second. Kailash, please confirm once my screen is visible. So this is my workflow. So after setting up a composite problem here, you take it to the static structural one, or and after this you can
model.
Yes, model. You can select it here, and you can bring your setup here itself, sir. Wait a second. This geometry. Yes. So directly you can take your ACP part into the model part. If you wanted to set up a problem as a pre-stress, then you need to add the solution over it here. Okay, so now this complete problem is a combination of a pre-stress vibration problem. So this will be the workflow for it. Sorry. I hope.
Then I think we have to follow the same procedure what we saw in the model analysis, and
yes.
Completely same.
Okay, and any other questions?
In the meantime, I have shared a feedback form link in the chat. So I request everyone to please provide your feedback. So it is important for us to improve ourselves. So definitely, give your feedback over there. If any concern is there, anything you need, specifically for your institute, that also you can mention over there. So we can discuss on it later on. So just provide your feedback in this feedback form which I have shared just now. I can see only 4 feedbacks I got. So I request like many people are available. So just provide your feedback. So definitely that can be helpful for us. Thank you.
Thank you to Shah Sharma sir and Kailash sir for giving such a good knowledge on this hands-on training. Hope we meet again, and thank you participants for cooperating. Thank you, sir.
Thank you, ma'am.
Thank you, ma'am. And thank you, everyone. So,
Sir, please, can you please give your email, sir? Tushar Sharma.
Sir,
Yes,
my
sir. I
mail
have
ID is
posted his mail ID. Yeah, you can check it out.
okay.
Please give your mail ID, sir.
Yeah, it's given, sir, in the chat. You
Ah,
can
okay, okay. Thank you.
Okay, thank you so much, everyone.
Thank you, everyone.
Thank you,
Thank
sir.
you.
Thank you, sir.
Organizer. Thank you, participants.
Thank you,
Thank
Jagtap
you,
ji,
sir.
Tushar Sharma sahib.
Thank you, sir.
Thank you very much, sir.
Sir, if you can circulate this feedback form in WhatsApp group, if you have, because many people have not given the feedback over here, so it will be better for us also if we get feedback.
We will give, sir.
Yeah.
Okay, sir.
Yeah.
I
Okay.
will share.
Okay. Thank you so much.
Thank you.
Thank you for giving the opportunity, sir. Thank you.
Welcome, sir. Thank you, participants. Our next session will start tomorrow at 10 a.m. Thanks.
Thank you.